Welcome back to the DemystifySci podcast. I'm Anastasia.
I'm Shiloh.
And this is the podcast where we search for the theories that are going to change the world. What this means is that every single theory that we present here is not necessarily going to change the world, but some significant fraction of them are absolutely dramatic, incredible pictures of how we will see nature, economics, history, archaeology, all of the above in the next few decades. And today we have a conversation that is one of those theories that we absolutely believe is going to change the world. And I don't think that we have to wait very long for that change to come. The idea that's going to change the world is the fact that we are wrong about the structure of the sun. Everybody right now, for the most part, thinks that the sun is a gaseous plasma. But it turns out that when you start digging into what we see when we look at the sun, when you explore its spectrum, when you see that it's a continuous spectrum, that is an absolutely perfect black body, which only comes from condensed matter, you suddenly start to realize that perhaps everything that we think about the sun, everything that we think about the stars, maybe even everything that we think about the Big Bang and the age of the universe and almost all of astrophysics and cosmology is not actually the right story.
Not only that, but if we don't understand how the stars work, then what are we doing trying to build little stars, in other words, fusion reactors, here on Earth? Well, it follows that we might want to rethink that process as well.
For the conversation, we have two of our absolutely most favorite people, and also people that we're proud to call mentors. We have pierre-marie Robitaille, who built the world's first 8T MRI, and we also have Jim Keller, who has been a computer architect in Silicon Valley for more than 20 years. He has built at AMD, at Intel, at Tesla, at Apple. Now he's working on open source AI chips at Tenstorrent. He is also working on producing tabletop semiconductor fabrication devices so that companies can produce them in-house as easily as today. They can 3D print some component that they need for a machine. These two people are absolute intellectual giants of engineering and science, and today we brought them together for a conversation about the liquid sun, about the future of cosmology, about the differences between science and engineering, how to come up with incredible ideas, what it takes to build something great, and why incredible science is so hard to find.
And we investigate the death cult at the heart of modern cosmology and astrophysics. Jim is not only an incredible engineer, but he's also a great patron of the sciences, and Jim actually made it possible for us to begin planning this conference in Sesimbra this summer. And originally we had planned on having Pierre at the conference as well. Unfortunately, Pierre wasn't able to travel, so we figured, why not introduce them to each other and see what happens?
If you want to come to Sesimbra, Portugal, to Beyond the Big Bang and see the incredible slate of conversations that we have lined up with everybody from Gareth Samuel of See the Pattern, Alexander Unziker of Unziker's Real Physics, to C.S. Unikrishnan of India's LIGO project, including Eric Lerner, who kicked off this entire modern revival of the idea that the Big Bang never happened by publishing a book with the same name back in the 90s. It's an incredible weekend. We have only until June 1st for anybody who wants to come and have dinners with us. So if you want to come to Portugal and you want to come to the dinners Thursday through Sunday, get your membership as soon as you can, because on June 1st, those sales close, and then you are on your own for meals. We'll hopefully see you there.
Remember, even if you can't make it to Portugal, the only way that we fund this project is through you guys, which means we work directly for you. So if you're already supporting the project, thank you. If you're not yet supporting the project, remember, you could give 75 cents a week and make sure that we can continue to put all of our time towards this and bring you guys more and more of what you already love. So check it out over at patreon.com. And
enjoy the conversation. It is a real one with two absolutely incredible minds, me and Shiloh moderating. And we hope to hear what you think about it down in the comments. We'll see you on the other side.
The scientific revolution starts now.
The DemystifySci podcast.
Let us see in the dark.
Why does it matter if we're wrong about the way that the sun works?
Why does it matter if we're wrong?
Yeah, like so it's not a gas, and it's liquid metallic hydrogen, and we've been wrong all these years. Like, does it change things substantively?
Yes, I think it does change
Okay.
a lot. I mean, obviously, man is trying to do fusion now with the ITER project, for instance, in France. And of course, that project will not pump a single electron into the grid. It's an experimental project, right? But and they're trying to confine a plasma using magnets doing that. But I don't think the sun is operating that way at all. It's got a lattice, and the lattice is helping the electron, the nuclei to fuse as they're vibrating within the lattice. So the nuclei are already aligned, and they're already getting ready to fuse, as they vibrate, and then eventually they just tunnel through and fuse. So it's a completely different setup. And so if we're going to have successful fusion on Earth, I think it's important that we do rethink the sun. But it's not only important economically for mankind, it could be very important, but I think our understanding of astronomy will dramatically change. And so if we study astronomy because, that it helps us to understand our place or, to understand the universe better, well, if we've got it all wrong, it's not very good at understanding. So I think to understand that the stars are condensed matter, that has great implications, not only for the sun, other star types, what are white dwarfs really? Are they ultra dense? Are they not dense? So I've said that the white dwarf just has a different crystal structure. It's condensed matter. It has a different crystal structure. And that's why it's not as luminous. It's not because it's small. It's because it just can't emit as well. Just like a diamond and graphite both have about the same density, but they have a very different crystal structure. One of them, graphite, is a perfect absorber, or close to perfect, and the other one's transparent. So that's the same thing that's happening. Why is the luminosity of the dwarf low? It's because you have a different lattice. So it helps us understand, the different star types, and our complete view of astronomy will change if the sun is condensed matter. That's why they say that the sun is the Rosetta Stone of astronomy, right?
Mm.
Once you understand the sun, it touches everything, all the other star types, and
I want to know why it matters to Jim too. Obviously, Jim's been attracted to these ideas, and I think
there's two funny ones. Like, one's a meta narrative, which is my belief is most of modern science is wrong, either fundamentally or incrementally wrong. Like, you could have a measurement where your theory is pretty good, but you're not accurate enough, for example, or you could have a theory that's just plain wrong. And the sun is really interesting because it's relatively close by. It flared, the Carrington event in 1859, I think it is, melted wires in the telegraph system. And it wasn't a particularly big solar flare. Like, they get 100 times bigger, right? And so there's, like, again, when science is wrong and lots of people are working on wrong theories, it's kind of a waste of effort, and science has been wrong about, like, everything. Like, the Ptolemy theory of, the solar system went on for thousands of years, and many, many physicists became trained in that. They did really great calculations, actually, which advanced some kinds of mathematics. But it was kind of a wild thing to think of all the senior physicists who studied the solar system for 1,000 years in universities were studying a fundamentally wrong thing. Now imagine if they had a better theory, right? They could have made more advancements, because the problem with wrong theories is while you can refine them and curve fit them better, it's not as expansive as a good theory that's better match. And the other thing is, if we don't understand the sun, it will be really a drag, for a big solar flare to knock out society. And the probability of understanding the sun properly with a wrong theory seems low, right? And now whether we can do something about it, who knows? I'm a fan of, if you have a real problem, some substantial number of people should be working on it. And I don't think you can solve that kind of problem or predict what the sun is doing if your theory is fairly wrong.
So before we get deeper into the question of specific aspects of the sun, I wonder if we could take some time to talk about the link between science and engineering. Because both of you are engineers.
Oh.
No,
Deep-
I'm a chemist by training.
That's true, but you built...
I assembled an AT, but yeah. I mean, I have great respect for engineers, and I did a lot of
Yeah,
engineering, that's true. And when I was a person that didn't want to just be in the lab theoretically. I mean, I was in the laboratory when the AT was assembled. I was part of every step of assembling it. I was always in the laboratory. I was not at my desk, and tried to guide every step. And so in that sense, I guess you could say I'm an engineer, because I actually, use oscilloscopes and network analyzers and all the things you use in MRI. So yeah, so in that sense, I have a respect for engineering. That's for sure.
And I would say I have a respect for scientists.
So that's a good starting point.
And since we've just talked for many hours, the last day or so, Pierre is definitely a scientist. He has a talent for engineering. So in the course of his investigations in the MRI, he figured out a bunch of stuff and then learned enough engineering to go help build a machine. I'm an engineer. Like, I was putting things together as a little kid. And in college, I did well in math and science. But like, compared to real mathematicians, I didn't know anything. Compared to real physicists, I didn't know anything. I'm an electrical engineer. My instinct is always to make something. Like, I love programming because I could think about an idea and see it, then program and then watch it work. Like, it's not that fundamental. Like, computer science is awkwardly very simple. We just count to 1 over and over. 0, 1, it's binary. So it's not deep science technically. There's a phenomena of, we were talking about this, of the complexity of modern computer science is really high. And to successfully build a computer, you have to partition the problem and also partition the team and build proper abstraction layers. These are engineering solutions to like a complicated task, to achieve a known goal. Like anomalies are interesting, but if we don't have to deal with it, we just walk right past it.
Oh, that's so interesting, because breaking down complex problems into these small teams for science is sometimes a disaster, because you get these teams working in isolation from one another and they don't have a wider view of the big picture.
Yeah, so in an engineering project, like TenStorm right now is over 800 people. It's technically 100 teams, right? And then they coordinate. And at various points, the teams coordinate together. And since we're making something useful, like software that works, or a chip that functions, or a business plan that operates, or a supply chain that coordinates with an engineering release date, we're constantly bringing the pieces together in, like, say, a falsifiable event. Like, it's going to work or not. And we know it all the time. So in a good organization, people own things with some clarity so they can do them. But they also, I joke that it's all input, function, output, right? And those things have to solve properly. And big companies where, say, they make too much money for a while, or they have a captured customer, they can do engineering projects that essentially have no falsifiable endpoints. And then those things go off track.
Anything?
What's that?
Like, they just never deliver anything?
Oh, some big companies, they make a new product every year, and the people need the product. So the engineering teams are engineering features and all kinds of things that nobody actually cares about, but nobody notices.
Interesting.
Like, does anybody care which iPhone they have anymore? Nobody cares. They make a new one every year.
Yeah.
I don't know which year my iPhone is. It used to matter a lot. Every new iPhone was a big step. Now, iPhone 14, 15, 16. For most people, they're the same. Like, there's some spec that changes. Apple will tell you it's 2x better. But nobody cares. So that's become like a not falsifiable output.
Okay. And so in the process of going to the lengths of engineering something, it seems like the difference between science is that it is exploratory and engineering is product focused.
Goal-oriented.
Okay. And so is there a place...
There's also this element of the meta-narrative that Jim mentioned, perhaps incidentally. The science does guide the meta-narratives that we use as a civilization. Yes. And, for me, and I'd be curious for Pierre to weigh in on this, the meta-narrative of cosmology and astrophysics is very bleak right now.
Right.
Dark matter, dark energy, black holes. Like it has this kind of
The heat death of the
it
universe.
has a very deathful feel to it.
That's right.
Which seems like it shouldn't matter that much, but it also is kind of like a flag we're waving as the civilization, right?
It's something that actually bothered me about the Vatican Observatory. I've never talked about this before, but of course, after Galileo, the church decided to invest in astronomy. And there was a very famous astronomer, Angelo Secchi. He wrote a book, Le Soleil, in French. And even if you can't read French, if you get a copy of the Soleil, you can get it at a university library. Just look at the illustrations of what Secchi had drawn about the sunspots on the sunspots and the characteristics of the sun. It's unbelievable. But Secchi was a great astronomer. But since then, what has happened, and I've met people that worked for the Vatican Observatory, and because of Lemaitre, who was a Jesuit, I don't think he was officially associated with the Vatican Observatory. I think he was at the University of Louvain in Belgium.
This is the father of the Big Bang.
The father of the Big Bang was an astronomer. And he was a Jesuit priest. And of course, they had this link of, okay, well, God, pointed at the universe, basically. I mean, it fit into the creation narrative of the church that, and actually, I think it was Pius the 12th. He loved it so much, he was going to use papal authority to say the Big Bang was real. Like he loved the theory so much. And finally, the cardinals around him said, well, you can't do that. That's beyond papal authority. This is a question of science. But what has happened is that this love of this idea of God, like pointing to a spot, and then there was a primordial atom, and it exploded and made the Big Bang, and people in the church loved it. But I always thought it was presumption. We will never know how the universe was made. That is just presumption. And then people think, well, Pierre, you're unscientific by saying that. No, I'm realistic of what is the potential of the human mind. You can have all kinds of ideas, but what is your probability that you're going to be ever correct, or that we can understand how all of this came about? We can look at it, try to analyze it, but my personal opinion is we will never really know. And one of the problems with the Vatican Observatory, and I think it's a little bit harsh to say this, especially as a Catholic, to speak against the Jesuits, but they've embraced this darkness. And that's what Shiloh was referring to, that we live in a dark universe. It's 95% dark matter and dark energy. And I just can't understand why a priest would want to live in a dark universe. So I'm just telling you that this darkness, that we live in a universe of darkness. And, that has philosophical consequences. I think it has spiritual consequences. So, people will say, well, gosh, Pierre's a religious nut. He thinks that, this has got all religious overtones. But people don't say that about the Jesuits. When they're happy with their theory of the Big Bang, they are willing to say, oh, well, they're not religious nuts. We accept all that. So I'm against it. I think philosophically it's quite wrong. And I think mankind needs to move away from it. And I think it will when they lose the microwave background, they will move away from the Big Bang. Finally, it'll be over.
Yeah. So on the darkness thing, so humans are animals, and animals are generally zero-sum game evolved. So the game theory we operate in is, if you're in a forest and there's a limited amount of food, if I eat, you don't, right? And in certain times of human culture, there's big optimism. Like post World War II, there was a huge technological expansion, and people were actually quite optimistic in the 70s and 80s and 90s. And then it sort of started to plateau there. But our defaulting is we're running out of stuff. And I have people who say there's no place to build. And I always ask them, have you been in an airplane? 99%. Like in Silicon Valley, everybody knows they're out of land. It's all locked up in conservation areas. And it's nice to have those. But if you look at the state of California, it's huge. Another 100,000 acres to build condos would be fine, and nobody would notice it from space. So we have this I think, intrinsic narrative about zero-sum game behavior, which manifests in kind of a weird negativity, as opposed to like an optimist thing, which is we live in a bountiful planet with lots of atoms, unbelievable amounts of energy, lots of people. I'm a big fan of lots of people who should be ideally doing the most thinking and the most fun things and interesting things possible. And most people's narrative is we're running out of stuff. It manifests like peak oil. We're going to run out of energy. Well, we're going to run out of sunlight. Like the sun is amazing. It's such an energetic thing. And the same with the universe. The universe is clearly self-organizing. Like you can see there's structures now 1 billion light years across, right? And there's galaxies and threads of galaxies, and like it's so amazing, and it's bright and full of energy. Like the universe is very energetic.
I wonder if it doesn't reflect the climate of increasing scarcity inside the academic communities that are repairing the decrepit.
Yeah, and that's so interesting because the funding for universities is going way up, but it's all going into bureaucracy. So the bureaucrats then decide, what should we squeeze? The bureaucrats? No, we never squeeze those, right? And the bureaucrats say they're delivering all these services, so all the professors are getting squeezed.
Right.
And part of it is, but of course you're getting squeezed, we're running out of everything. And that's pervasive everywhere. And why would we be running out of everything? Humans are unbelievably productive. And you only run out of things if something is diverting those things to some useless course, like maybe bad science, bureaucratic endeavors, corruption,
Well, science that's been chewed on and chewed on and chewed on is safe science as far as grants are concerned, right? Yes. We want to add another significant digit to this measurement or another energy level of particles.
I like that.
But this links me back to the original question which set us on this path, which is, what is the line between science and engineering? Because I think that that's not always clear, because we've talked to Jim, to you a ton about the fact that yes, there's theories for electromagnetic radiation and Maxwell's laws and like all of these things that are really, really functional. But then when you scratch at the surface of it, you end up at quantum mechanics that is not really explicatory. And so it seems like we're capable of building and doing tons of engineering without having a scientific foundation for those concepts. And so where does it become necessary?
We currently have zero legit scientific foundations for anything.
Do you think it's that bad? Like,
yeah. We don't know either space or time or gravity or matter or particle or fields. Like name one that's really solid. Like there's theories, but and I really liked your guest, the shadow science guy,
Adam K.
Right, because he walked through about how numerous times you weren't allowed. Like Newton was asked, like he came up with the equation for gravity. He said, "What causes gravity?" He said, "We can't know." Right now, Einstein thinks he came up with a solution. The same with heat. It's like, is it a fluid or a vibration? We can't know, right? Pierre, you just said it's possible, or you think humans won't be able to describe, how the universe came about. I actually think all questions where you say, we can't know are probably wrong, right? Like what causes electromagnetic field? Why is spin so weird? Like there's equations that sort of describe it, but they all, like math is infinite. Math is beautiful. Right. And if you have enough data points, you can come up with math and curve fit to anything. And then you can say the math predicts spin.
Well, the problem with
you would have never predicted spin for math in general. Right. It's all guided by some observation. So
well, it's interesting because you can say that it predicts spin because you have parameterized it sufficiently on the basis of observations, but the theory does not in and of itself provide for the necessity of spin as a feature of the
in principle,
universe.
A good theory is you have some data, you make a theory. The Kuhnian theory of science, or Karl Popper's theory, is you get some data, you make up a theory about it, and then it makes additional predictions.
Right.
And if they're right, you're happy. I don't believe modern science makes many predictions. But it makes a lot of curve fitting.
Right, a lot of patchwork.
Yeah. Like the James Webb Telescope has all the astrophysicists off patching up all their equations because, every generation there's a new telescope. My joke about this is the universe used to be 3 billion years old, and then 6 to 7, and then 12 to 13. And the universe is basically 500 million years older than the best telescope can see.
See?
So when James Webb solve further, like I'm predicting that the new age of the universe will be 27 billion years old.
And that's part of the problem of why I said we'll never know.
Hmm.
Because as our telescopes ever get better, we keep looking further, and then we keep discovering that the universe is ever so much greater.
Yes.
So how could you solve this problem? Do we live in an infinite universe? Is it finite? These are fundamental questions that mankind's unable to answer. We will never know the answer. Is it finite or infinite?
Well, I'll take a bet on that.
You'll take a bet?
I think all questions describe where the answer is. You can't know. It's something we should work on.
Yeah.
Like quantum mechanics, it's like you can't know this, and it's like, yeah, we couldn't know heat, we couldn't know gravity, we couldn't. There's a whole bunch of things we couldn't know.
Yeah.
Now the reason the reason that I differ a little bit. Now, first of all, the point I wanted to make was when we talked about darkness, I never made the point that everything is light. We actually live in a universe of light. All the astronomers are monitoring signal that is coming to them as electromagnetic radiation at whatever frequency. It's not always in the optical. But we live in a universe of light. Yet our theory is now 95% dark matter and dark energy. It's crazy. Now, why do I differ from Jim a little bit? It's not that I don't want people to think about these problems. They can. Everybody is welcome to invest where they want to put their life's work in. But in terms of how we expend dollars, that's a different problem. So when we had the Horizon well problem in the Caribbean, you remember a few years ago, right? We couldn't go plug the well. So mankind wants to do all these very great adventures, and we can't even understand our own planet properly. So I want to see things that, there's starvation on Earth. I want to solve local problems. And I think it's very dangerous to dream too. It's okay to dream, but you can't make everybody dreamers. I mean, you have to solve real problems on Earth. There are people that are dying on this planet, and that's a reality. And that's why I have a very conservative view on these things. When you see starvation, you cannot ignore it. And we do as a society because we're putting our money in these grandiose ventures. And so I guess that's almost unscientific to speak that way as a scientist, but it's a reality of the human condition. We have neighbors and we have to think about them. We can't just be thinking about our ideas.
But this is where the size of the check is inversely proportional to success. So like most of the great scientists of the 1800s and early 1900s, were underfunded.
Right.
Or independently wealthy.
Or had a patron or something.
Or were like counts
really
or lords or landed gentry.
I have friends who are well-traveled in Africa where there is starvation. And when the UN and US government goes in with big checks,
I know nothing happens.
The local chiefs get new vans, new trucks. Right. And all like the big water projects and sewer projects in Africa funded by big money fail because the big project doesn't have sufficient resources to actually manage it. Where meanwhile, local development, like in Kenya, and I've been to Kenya and I have some friends there, it's really great.
Right.
And almost all the really great things that are actually uplifting people are underfunded local efforts and all that. So my magic wand would be to eliminate big dollars. If your science costs more than $1 million, you're probably wrong. And it's probably never going anywhere.
What about like large scale detectors? Because $1
million, by the way, I want to say is not too much today in science. I have to tell you that back when I was doing heart research, everything has become so expensive. I mean, $1 million grant today would be considered small in the medical circles. And it's unfortunate, but it's a reality. So,
well, maybe it's like, what's the budget per person? Like the big particle colliders, they suck up billions of dollars, and lots of people focus on one narrow goal to prove a theory, which, who knows if it's true or not. And that really vacuums up a lot of attention. And I've seen this in computer design. Like I used to have this graph where the time to do a project was inversely proportional to the number of people. So 100 people could build a computer in 2 years, 200 in 3 years, 400 in 4 years. And 500 people could never finish a project. And then Intel had a team of 800 people, and they finished the project. Not very good. And what happened is several hundred people doing the actual work detached from the organizational superstructure, and they finished the project despite the management team, which was really great.
Wow.
And I know because I hired a half a dozen engineers from that project into a startup. And one guy was describing this thing he did, and he said, "What do you think?" And I said, "I'm amazed." And he goes, "Why?" He goes, "Well, it's completely unnecessary. Like, there's a way easier way to do this." And he goes, "I thought so. But you made it work. I think you're a genius." Like, I hired him. He did great work. So the problem with size is humans, in large masses, absent some really strong, organizing principle, inherently waste money. Right?
There's probably
fail to solve things like, starvation and health issues.
Right. I'm not saying we're going to solve these problems with big groups and stuff, but I think we do have to focus on some of the problems that are here on Earth. I mean, I'm not advocating to spend fortunes in all these areas. I realize that when you give a lot of money to countries, I mean, my uncle used to bring grain, Canadian grain, to starving countries, and the grain would just be offloaded from one ship to another and then sent and sold by that country so that the rich people in that country would get even more money. They wouldn't even give it to their people. There's all kinds of crazy things that happen in the world. So I understand that. I just think that astronomy has benefited from billions and billions of dollars, and a lot of it is for ideas that just don't make any sense. And the problem is they peer review themselves. So when they ask for their money, their friends are peer reviewing the papers or peer reviewing the grants, and they say, "Yeah, let's go for it. Let's give another few $1 billion on this effort." Yeah. And I think that society needs to say, "Hey, we need to calm it down on just permitting scientists to just spend money at will on things that aren't going to help humanity."
Okay, so this is actually
so I'm a little tough on it, but
it gets back to the engineering question. Mm-hmm. So good engineering projects, there's a reason. Like, we need to build a bridge; it needs not to fall down. Or my company's building a computer that competes with somebody else, and the marketplace will, somewhat decide which one is better, faster, cheaper, and having those endpoints. And then I make a joke about this. Like, there's, correct and incorrect in the 2x2, and falsifiable and not falsifiable. So as a scientist, correct and falsifiable, it's great. That's a testable theory. And incorrect and falsifiable, that maybe you learned something, maybe you wasted a year of your life and you found out your thing was wrong. Non-falsifiable becomes, buddy review. Like, people think this is correct and they think that's not correct, but it's not falsifiable. This creates a weird selection bias for non-falsifiable science. Because if you're going to do something and you're worried that it might be wrong, doing something that can't be proven wrong, good deal. It's a funny thing.
Right.
But a lot of modern, physics and science and astrophysics is not falsifiable.
But isn't it because you have to start with some collection of things that are true and then build from
Well, we don't know how do we define true. I mean, if you look at the astronomers, they deny the surface of the sun. I mean, to me, that's unbelievable nowadays. I mean, how did the sun become a gas, right? But in 1864 or 59, I think, Herbert Spencer first made the gas bubble. He had a bubble model of the sun, and there was gas inside, and it has an outer bubble. And then Secchi and Fay went with it, and then Lane finally in 1870, the sun kind of became a gas at that point. So, how did it become a gas? Well, and Fay writes famously in his paper that, he's looking at the sun and he decides that it's a gas. How did he know in 1864? And so it stayed in astronomy. We've denied the surface of the sun to this day. And to me, it's incredible. At every frequency, it's not only in the optical. I mean, they tell us the surface of the sun is an optical illusion. It's not an optical illusion. We see it at every frequency, from the subaudio all the way to the gamma. We see evidence of a surface of the sun, yet they still deny it. So if we can't even get that right, And then they try to, it's an interesting thing about astronomers. They try to they share to the world their discoveries, and yet they're unable to take any criticism at all when somebody says, no, this cannot be right. There is a problem here. And so this again goes to, they review themselves, and then they keep promoting the idea that the sun doesn't have a surface. And I think if I take you to a lake and I say, well, do you need to know what the lake is made of for you to know that that is a surface? It has a surface. Why does the public not call them on it and say, hey, the sun has a surface. Enough is enough. It's condensed matter. It's over.
We should at least be consistent and say that lakes are optical illusions.
Yeah,
that would be better. Or like Wikipedia is funny because there's a phase diagram of hydrogen, which is easy to look up. And then it turns out when you look up a lot of them, you find out there's lots of variations because most of the phases have never been reproduced. They're theoretical, but let's imagine it has a diagram. The description of Jupiter and Saturn say it's obvious as you go down through the gas ball, the pressure goes up, and according to the phase diagram, it transitions to liquid hydrogen and then liquid metallic hydrogen, then to solid. Right, but on the sun, that's not allowed to happen for reasons, and both of them are published in Wikipedia. So, like, they're both hydrogen balls. They just one's bigger than the other, as best I can tell.
The metastability is a really important piece of that puzzle when I discuss this with people as well. Because if you try to map the phase diagram onto the surface of the sun, it doesn't quite work out, right? And so you have to bring in this idea of metastability.
Alexander Unzicker did the calculation about, according to the published phase diagrams, where it happens.
Yeah.
Like, but that assumes that the atmosphere of the sun actually gets quite dense, and then it goes from transparent molecular hydrogen to liquid hydrogen, which is not transparent. But he published that in a book called The Liquid Sun, I think, based on Pierre's work. So I don't think he said there was a big problem with the phase diagram.
I think the pressures necessary to form the liquid metallic hydrogen should be a bit deeper than the surface of the sun.
It should be formed in the interior and then rise to the surface.
Kind of bubbles up.
And it's like a diamond. So it's like a diamond, right? We make a diamond in the interior of the sun, of the Earth, and then the diamond that comes up and it's stable, so it's metastable, but it takes high pressures and temperatures to make the diamond. And
diamonds will fall apart into graphene eventually.
Right.
And my prediction is the phase diagram's wrong.
So
as an engineer, I think, let's go measure everything. We can make probes that can get really close to the sun. We can do way better sensors. Like the sun's technically not that hot. What's that?
But you think that's hard to do for $1 million? Though?
No, actually, we just designed a satellite this morning for $100,000. Here's the really wild thing. Again, so the world says going into space is really hard and complicated and expensive, and space is, somehow empty and simultaneously dangerous and a whole bunch of stuff. And SpaceX is firing rockets every week. Like, it's hilarious. And their cost goal is sub $1,000 per kilogram. So now getting something in the low Earth orbit is going to be relatively cheap. Now you need to make boosters to get out of orbit. But how much does a sensor cost? Nothing. It's a computer chip. Like, all sensors just detect electrons and electromagnetic waves. Like, they're not, there's inertial sensors. Like, the family of sensors is small. We could probably make a small sensor for everything we need and put it on this table. And it has to go.
You think we can touch the surface of the sun?
I don't know. It's not that
one of the things that we do know.
Or is it?
I mean, when I was a child, people told us about the gas giants, Jupiter and Saturn, and that they're gaseous. And I don't know, it was about 10 years ago that the comet went and hit Jupiter, and it sure imploded on impact, right on the surface. It just exploded. So Jupiter is not just a gas giant. I mean, it has the right density to be condensed matter. I mean, the problem with their idea is that these are gas giants or gas planets is their densities aren't right. The densities, the average density of the sun is 1.4 grams per centimeter cubed, and the gas giants,
which is like water, by the way.
Which is like water, and water is 1, and the gas giants are about 1. I think one of them is about 0.7, one of them is about 1. I can't remember exactly, but they're all about 1. These aren't gases. And so we just need to call them for what they are. I mean, it's enough of this stuff. I mean, it's been 200 years it's almost 200 years that we've been stuck in this paradigm of gaseous objects in astronomy.
So then
it's been what? We're 170 years into it. That might be enough now.
So walk us through the 100 grand satellite or the 100 grand probe to go measure the sun. Like, what does that actually look like?
We weren't measuring the sun. We were going to L2 to measure the microwave background. We wanted.
Let's imagine we make a prototype satellite. So maybe it's a 0.5 meter by 0.5 meter. And inside it, it's a battery pack, a computer board, and some small array of sensors. So what do you want to measure on the sun? Temperature, pressure, electric field, magnetic field, gravitational field. All those sensors are small, like inertial sensors. Like every one of those things is small. And then the temperature, you can correct me, is reported, to be 5,700 degrees, which isn't particularly hot. Now, most materials will melt at some point at that temperature. So you have a time frame. So you have to build a satellite with some way to cool it, and you have to go pretty fast. You're not going to land on the sun and sit there and do experiments. They landed a satellite supposedly on Venus, the Russians did, where it's 800 degrees and it operated for a while. So none of the components are expensive, right? And you don't build the components mostly to withstand the high temperature. You build a heat shield to protect them from the high temperature, right? So as you're going there, you want something very reflective so it's not absorbing any energy. And you want to drive the satellite low, and you want to do a lot of small satellites. Like the weird thing about like the Hubble and the James Webb is they're amazingly accurate, right? And they spent a lot of money doing it. Now the question is, if a company like SpaceX designed a next best, better James Webb telescope, I promise it wouldn't cost $1 billion.
Sure.
The budget would be $1 million, and they'd spend $2.5 million, and it would be great.
Okay,
but our actual design was to go measure the microwave background at L2. We weren't talking about the sun. But interestingly, Dmitry Rambutsky, who was the first editor, he's the editor-in-chief of Progress in Physics, where a lot of my papers were initially published on the sun. And he had a dream of sending a probe just to go and pound the sun. Like all he wanted to do was look at this probe and design a probe that would go and hit the surface of the sun.
Oh, that'd be great.
And so no instruments. He just wants to send a ball.
You just have to throw a rock at the sun.
So throw a rock at the sun.
All right. So there's our prototype. So it needs to be big enough so it doesn't fully ablate on the way in. We need to propel it fast enough. We have the high enough resolution cameras to see pretty small objects at the surface. What's the current resolution of the?
I think it's not small enough now. I think it's still 10 kilometers or so.
All right, so we have to get a camera closer to the sun. Oh, so here's the thing. We send the rock, and behind it, the cameraman.
Perfect. I like
right?
that.
And so we stick.
So all right, see, there it is. An engineer has come up with the good answer.
Yeah. So you're saying the resolution is not high enough. So then we go, this is just a camera problem. Yeah. Like how close does it have to be? And then what's the temperature profile look like? And then how do we make a camera big enough to be far enough behind the rock so it can see the sun?
So now let's talk about the temperature profile, because Jim wants to get his rock into the sun. So, the astronomers are telling us...
inertial sensors and everything else.
The astronomers are telling us that the corona is at millions of degrees, and it cannot be. The continuous spectrum, I was telling Jim yesterday.
That's right.
Lean a little bit closer to this.
You're leaning out of the camera.
I was telling Jim today that the sun's continuous spectrum, the corona actually has a continuous spectrum, and it reddens away from the surface. That's been known for 100 and some years. 130 years or so, that if you look at the continuous spectrum of the corona, not the E spectrum that is the line emission spectrum, but the continuous spectrum is showing reddening as you move away from the surface. So the corona is actually cooling away from the surface. It's not at millions of degrees. The reason that we see millions of degrees, or they interpreted it as millions of degrees, is the corona is electropositive, and any element like iron that touches this electropositive material will be stripped of its electrons, and then the electrons are channeled back down to the surface. So now you get iron 23, like highly ionized iron up in the corona, and they say, oh, well, the temperature's there to make that in the laboratory. We need temperatures of millions of degrees, but that's not how it's made. It's made with a chemical reaction, so the temperatures are not this. So this is another thing.
Can I throw in like a little anecdote that's kind of interesting? One of the early interviews we did on this channel was with Nikki Fox, who was the director of the Parker Solar Probe project. And one of our first questions was something along the lines of, "Wow, if the corona is millions of degrees, how are you flying a spacecraft into that?" And it was funny because seemed to be a question she hadn't quite struggled with before. And so you could see her brain kind of working this out in real time, where she was like, well, there's not that many of these particles. So if you will have one particle in, a box and it's moving really, really fast, the temperature, technically average kinetic energy, is unbelievably high, but you're going to be very cold still if you encounter that collision. Right. And so the concept of temperature starts to, and this is something, Jim, we've talked about a bunch.
I love the Wikipedia page on temperature, because you think temperature, when you grow up, is the thing you read on a thermometer. And then in chemistry science, you often put a thermometer in like a beaker of something, and you kind of have this idea. And then in physics, they start telling you it's vibrational, it's kinetic energy. If you get into quantum physics, then it's a population of states, and it's about electron orbitals. And they get to 0K, the atom stops moving. Like, so many things happen. And the Wikipedia page is epic because it's pages of temperature describing very different phenomena with many hyperlinks. And then, so temperature becomes but it's also super useful, just like energy is super useful, because energy also has many forms. And once you say joule, you think you can say A equal B equal C equal D, even though the phenomena are completely different. And it's sort of, as an engineer thinking, it's like useful to have a temperature. But sometimes, like I worked on a project where we had atoms at low pressure, and it was like, what does temperature mean? Like, what happens to a gas when it's low enough pressure that it's not collisional, right? And the answer was, don't know. Like, essentially, go do experiments to figure out what happens.
Well, this is part of the siloing phenomenon in science, right? You get these words that are very context dependent. I think plasma is another great example of that, where each scientist working in their own domain has a different connotation for that word, which is specific to their domain.
Right.
And then when they try to discuss between these tribes, people are talking past one another.
Also, they did an overgeneralization. So we're taught that there's, gas, liquid, solid, plasma. But the phase diagrams often have lots of states of these things. And then there's intermediate states, like a liquid metallic state and the ionized liquid metallic state. And it's sort of like, well, the simplistic version is sticky, like temperature is sticky, energy is sticky, the four phases of matter is sticky. But the reality of matter is way more complicated and interesting. Right. But people will take a concept like temperature, apply it to the ionization state of an iron atom, and then declare the sun is 10 million degrees, when that literally has nothing to do with anything.
And the backwards problem, it might be worth just sharing with people, because this was a fascinating conversation we had last night about the temperature of the surface of the sun, which turns out to be the temperature of the rays from the sun, which may be...
Yes, right, that's what Planck said.
This is great. And this is the Planck.
This is what Max Planck warned the astronomers in his book, The Theory of Heat Radiation. In there's a section where he says that the spectrum of the sun that you measure, the black body spectrum, has to do with the temperature of it's characteristic of the rays. It has nothing to do with the real temperature of the surface. And that it's inappropriate to set the temperature of the sun this way. Planck actually warned them. Nobody paid attention to it. Now, why did Planck warn them?
Can you lay out a little bit more, like what it means for the temperature of the ray rather than the temperature of the surface?
No, he says it's a property of the rays themselves. It's not a property of the surface.
The surface may have other heat.
Yeah, there's other
dissipation processes.
Yeah, I'll explain it to you. So Planck knew that to have a black body spectrum, there were certain conditions that had to be met. So you had no convection, no conduction. So when the astronomers are taking a temperature from the sun, they have to assume there's no convection on the sun. Well, is there convection on the sun? Obviously there is. It's quite visible that there's convection on the sun, both in the granules, as you have matter coming up from the interior of the sun and then rising to the surface. By the way, this is Baynard convection, which is a surface-driven process. That's one of the proofs that we have a real surface on the sun.
It's a bubbly-looking surface.
Yeah, it's a bubbly look. Well, it looks like oil that you put in a pan, and then as you heat it, it makes this Baynard convection. And the astronomers have even referred to that as Baynard convection, but now they try to move away from it because they realize that Baynard convection is a surface-driven process, and they try to tell us that there's no surface on the sun. Now, relative to what Planck said is you can't have convection or conduction and get a valid temperature. Now, I've expanded on it. I said, why do we get a black body curve? What is happening? And I've linked it to the vibration of atoms, of nuclei that are vibrating within the confines of a lattice. If you don't have a lattice, you'll never get a black body spectrum. That's why I've told people, whenever you have a black body spectrum, you have a lattice present somewhere. And so the atoms are vibrating, so the black body spectrum is produced by the vibration of atoms inside the lattice. But the lattice could also be moving. So what's happening in the sun is you have convection currents, and there's energy in those convection currents, right? So you get a certain you get a temperature which you could link to energy. So, E equals KT, that's the energy is equal to Boltzmann's constant times the temperature. This is a well-known little expression in physics. And so if you know the temperature, then using Boltzmann's constant, then you know the energy involved in that system. So, but that is only the vibrational energy of the system. What I'm saying is you don't have equipartition in the sun. So when you have a gas, chemists talk about there's different modes of energy. Energy is distributed in different modes in the gas. You have translation, you have rotation, and you have vibration. Like if it's a diatomic gas, the atoms are vibrating, right? And then, but the dipole, the diatomic molecule could be rotating. There's energy in rotation. There's energy in translation. And there's a theory called the equipartition theory that, the energy must be equally distributed in this gas in all these different modes. In vibration, rotation, and translation, we have equal partition of energy, equipartition. But that doesn't happen in condensed matter. In condensed matter, there is no equipartition. So you can have a certain amount of energy in the vibrational mode, which is what we see in the sun. We're seeing the vibrational mode of the sun as the atoms are vibrating within the lattice of the sun. But then there's also convection currents. Now, how much energy is in the convection currents? We want to know that. And what I've said is we can see it when you have a flare at the limb of the sun. When this occurs, we have gamma rays that are coming towards, or X-rays coming towards us from the limb of the sun. We see them. And the reason it's at the limb is that there's anisotropy there, that it's not emitting in all angles, but just preferentially in one angle. And at the limb, the angle is right so that it comes to the Earth and we see it, okay? Now, why are we getting X-rays there?
Super high energy light.
Right. And so what's happening is that the flare is breaking out from the sun. Material is being ejected from the sun. Is pushing away from the sun. And material that's flowing on the surface comes and hits it. And when it strikes, that's like hitting a wall. It's like striking a wall. And now all the energy is transferred from translational into emission, and now we see the X-ray. So what does that tell us? That the energy equivalent of the convection currents is in the millions of degrees. And that's why in the New York Times article I had written, the surface of the sun is at millions of degrees, but it's all trapped in translation. It's trapped in translation. We only see the vibrational energy is what we see from the spectrum. So I was I don't think people understood it. They must have thought, well, Pierre's a nut. The surface of the sun cannot be at millions of degrees. But there was a reason why I said it, and that is the reason that we have energy that's trapped in convection currents, which we're not sampling. And then we also have energy in conduction. We have electrons, so we were talking about plasmas. I said the sun is a one component plasma. You have a lattice where I'm talking a long time here. The lattice, we have...
You're not in a hurry, Pierre. It's totally fine.
I'm sorry.
No, take your
So you have a lattice, and the protons are...
Try not to tap the table quite so much.
Wonderful.
The audience is going to feel your emphasis.
Pierre, finish your thought, because I want...
So you have a lattice, and the electrons, the protons are arranged in lattice points, and the electrons are free to flow through that lattice. And so the electrons are delocalized, and you have conduction pathways through this lattice. So in the metallic hydrogen model of the sun, you can actually have conductors and insulators. The intercalate zones are insulators, and you have conductors in the metallic hydrogen layer, the hexagonal planar layer. So it's much nicer because it can help you explain why do we have magnetic fields in the sun. You have to have conduction that's controlled, electron conduction or charge motion in order to have this magnetic field. And how do you get that in a gaseous sun? You can't. So anyhow, what was your point?
Well, so you used the word temperature for the energy of convection.
You can link it to a temperature.
You can link it, and that was confusing me before. But you imagine you have a ball, and inside you have somebody swinging a very heavy weight. Like the weight doesn't get hot, right? It's just, but it can have a lot of energy. So a simple thought experiment is you have an iron box that's hot, and it has some black-body radiation spectrum, or maybe it's coated with soot. So you have black body, and then you have another box where inside it's actually not hot. There's a spinning weight, but occasionally it runs into something, which translates it to heat, which then can be put on the box. So the two boxes could have the same black body temperature, but one of them could have 100 times more energy in it because the convection holds energy in a really interesting way independent of temperature. It needs a method to translate the temperature, right. Which I really like if there's a large amount of convection energy in the sun and then it hits something, you can sort of get a gauge of how much energy is in that by what the emission is.
And then you have the conductive energy too, which is kind of like what you would feel if you grabbed a live wire, yes. I suppose.
Which you could also, you see the magnetic fields and you should be able to calculate this. So as an engineer, my brain goes to what sensors do we need, or do we already have enough data, and how do we start making the models to go figure this out? Because again, it would be useful to know how the sun works.
Which is a really interesting failure point of magnetohydrodynamics because it doesn't actually deal with the currents themselves on their face. It assumes the magnetic fields are baked into the substance.
and this is, especially science that we've inherited, right? So when you like I was taught Schrodinger's equation describes atoms, but we can only solve it for like a hydrogen. And maybe we can, maybe we can't. And then all sciences at some point become statistical, right? And statistical or curve fit, right? And that's useful, but you have to know the boundaries of it, because as soon as you're outside the boundaries, now you're talking nonsense, right? And like the magnetic fields of the sun are clearly very dynamic, and things are it's wildly intense, especially in flaring times.
So that is a really interesting entry point to a lot of the crises in astrophysics and cosmology, which is the exceeding of these boundary conditions, yes. Right? The famous who's the gentleman who did the Schwarzschild solution to the field equations, which opens up the door to black holes, right? It's obviously exceeding the boundary conditions of the theory for which it was designed. But all of the fun stuff happens when you go outside of physical reality and start to propose these exceptions that,
which are all untestable.
Of course.
By the way, I think Steve will tell you that it wasn't Schwarzschild, but it was Hilbert that made the mistake. It's not a Schwarzschild solution, but astronomers keep assigning it to him. But anyhow, I'm not an expert in relativity. If Steve was here, he would speak right now. He's not here. And he would defend,
I'm excited to say though that Steve will be coming by our house soon, and hopefully we can get the story.
Get it straight from him.
Yeah.
That's right. He's a person of great moral fiber, Steve Crothers, and that's something that's been missed on a lot of the world community that attacks him so much. I mean, Steve is just an unbelievable person. He's got such integrity, and I think he's an extremely talented scientist. And someday I hope that people come to recognize everything he's done for science. He's been invited a couple times to Russia to relativity meetings and has spoken about relativity, of his points on relativity. So he's well known, actually. And I think he can stand his own. There are some problems, and I think Steve has found some significant problems in relativity, but that's a side note.
He's the only person you've written papers with about these kind of things.
I write with. I'm very careful about who I write with. I used to write with a lot of people, and now I have a very limited group of people that I write with. I've written with two of my sons, and I write with Steve. Steve is a wonderful colleague. I flew to Australia one time. I was working on Kirchoff's law, and I had sent him a copy of Planck's book, or we discussed the copy of Planck's book. Then I had 2 copies at home, and then I flew to Australia to work with him, and we wrote a paper in 2 weeks together, which was kind of interesting. It was Planck had written a derivation of Kirchoff's law in his book, The Theory of Heat Radiation. And Steve and I started talking about it over the phone, and all the problems in Planck's derivation of Kirchoff's law, which nobody called him on. So Kirchoff's law, for people who don't know, it says that, within any opaque object, if you take an object that's opaque, that means light cannot get through its wall. Within that opaque object, if it's sitting at equilibrium, the radiation inside that object will always be the same, and it'll always depend only on temperature and frequency. And Kirchoff actually never did any experiments to prove his law. He just did it mathematically. But his law is critical for Planck because it gave a universal nature to Planck's constants. So to Planck's constant and Boltzmann's constant, they gain a universal characteristic. That's later in the theory of heat radiation. So in Planck's book, if Kirchoff's law is wrong, then we have no universality of these constants. And Planck had said that these constants will be measured even if you had an alien being in another planet far away, he would get Planck's constant. He will come to the same constant. And that is not true because Kirchoff's law is false. And that's one of the reasons that, if Kirchoff's law is correct, astronomers get to use Planck time, Planck length, all these characteristics that they use all the time in cosmology. They have a fundamental unit. That unit, nothing is going to be smaller than the Planck length, if Kirchoff is correct. If Kirchoff is wrong, then those units have no more meaning than a meter has versus a yard. Okay, so it's a big problem for astronomy if Kirchoff's law collapses. But the problem with Kirchoff's law is it was done mathematically. It was a mathematical law. There was no experimental proof. And then Kirchoff's own proof, his own mathematical proof, collapsed. So I think it was Hilbert in 1913 that said there's no valid theoretical proof of Kirchoff's law anymore. So then Planck, in his book, The Theory of Heat Radiation, he tried to formulate a proof. And then Steve and we started talking about Planck's proof. There were so many problems with it. I flew to Australia and we wrote a paper on the proof of Kirchoff's law by Max Planck. And I think the paper will stand up to the test of time. We did it right. And it shows that Planck's derivation of Kirchoff's law is incorrect. And so there is no proof of Kirchoff's law. Now, the beauty of working with Steve, we are very different people. I am an early bird person. I get up early and I start writing. Okay. But Steve is a night owl. So we basically worked around the clock. Like
Oh, that's right.
I would work.
The handoff at
Yeah,
at 3 p.m.
we hand off in the middle of the night. But it was such a pleasure to just be with Steve Crothers in Australia. Anybody who would get a chance to become friends with Steve would feel enormously privileged. He is just a wonderful guy. So that's my 2 cents.
Are there
on Steve
conditions?
Crothers.
Do you think there's conditions under which Kirchhoff's law is valid?
No, it never is. There are no conditions where it's valid. So if you look at opaque materials, one extreme would be a box lined with soot. That's probably a very good absorber as a natural absorber. There are better absorbers that have been synthesized than soot. And
This is like an ideal black body.
yeah, so that'd be like if you'd have a cavity and it's lined with soot, and that would be an ideal black body. But if you take a perfect reflector like silver, and you make the box out of polished silver, well, now even Planck recognized in his book, in the Theory of Heat Radiation, he recognized that a perfect emitter, it has no emissivity. That's by definition, it's a reflector. So Planck wrote in his book that the radiation inside the perfect reflector will be undefined. But then he writes, but if we put a little piece of carbon inside it, it'll thermalize the radiation and it'll immediately accept the right form. Well, that was complete nonsense. I hate to use that word when I talk about Max Planck, because people have to get me right here. Planck's equation is correct. Don't have a problem with Planck's equation. I have a problem with Kirchhoff's law. But when Planck put the little piece of graphite or little piece of carbon inside his box, and by the way, in the heat radiation, in the theory of heat radiation, he's inserting little pieces of carbon everywhere. It's constant. I wrote a whole paper on it of all the times that Planck has used a little piece of carbon.
Well, so he's creating a boundary condition where he's saying that by including this, all of a sudden you have something that you can look at and then read off of it.
Well, the problem is that when he puts the little piece, if you put a perfect absorber inside a perfect reflector, what happens? You have a perfect absorber. That's as if you had lined the whole box with graphite. It's perfect. What is the definition of perfection, right? So once you put it in there, you built a soot box. That's why you get the right spectrum. So the graphite is the key. It's a perfect absorber. So any ray that comes in and hits it will be thermalized. And then you get the right black body spectrum. So the problem with Kirchhoff's law is it's like when you take calculus, you have limits. You have a limit on the left, you have a limit on the right. Well, one of Kirchhoff's limits is the black body lined with soot, and the other one is the perfect reflector. But the problem is that on that side, the limit is undefined. Even Planck knew that it was undefined because you have 0 over 0 in Kirchhoff's law. You have absorption over emission, and it's basically 0 over 0, which is undefined, and Planck knew it. It's so that the law doesn't work. It's not valid. You have between the undefined perfect reflector and the black body, in the middle you have gray bodies. And like, he's an engineer, he knows that, and he's a communications engineer, or probably is aware of communication engineering a little bit, and he would know that, hey, we have microwave cavities everywhere. Our cell phones work because Kirchhoff's law does not work. If Kirchhoff was right, we wouldn't have cell towers. They wouldn't work because every one of these cavities that accepts the signal would be black inside, right? How do you make the simplest black body? You take a block, let's say of iron, and you drill a hole in it. And that makes you a very simple black body. If you sample the hole, it'll be black inside. If it's a graphite block, it'll definitely be black. If it's a reflector, it will reflect whatever is outside. So anyhow, the reason that we have cell towers or that we have microwave communication is because Kirchhoff's law is false. And so it's time.
Can you draw that more explicitly for me? Like, why is the falseness of Kirchhoff's law?
Because the box would be filled with black radiation if Kirchhoff's law was right.
As opposed to
so the noise power would just be huge inside the cavity. And that's not what we're seeing.
It'd be like self-illuminating.
Yeah. So it's just like an MRI, right? We build cavities in MRI, and this is what got me down this path of Kirchoff, right? If Kirchoff was right, perfect reflectors that we use in MRI they'd all be filled with black radiation, right? But they're not. Thankfully, they resonate. Inside a perfect reflector, you have standing waves, right? So when you have standing waves, you don't have a black body, which is, I'm talking too much, but that's what I was telling Jim yesterday. We were talking about the microwave reference load on the Planck satellites, and they have standing waves inside them. Well, if you have standing waves, that means we shouldn't have launched this satellite. The LFI was not working even when it was on the ground. It has standing waves within its reference loads, and that's published. I mean, I'm not just saying it. They are standing waves there. So black bodies don't sustain standing waves. So that's an important point. And so microwave technology would not exist if everything was thermalized inside a cavity. It's not.
And I think a consequence of the reality behind this invalidation is that emissivity tends to be ignored often. And when astronomers talk about, the Stefan-Boltzmann relationship, things like this, I've noticed it in my own astronomy textbook. I teach astronomy at the university, that it's disappearing from the relationship. Like you'll often see this nice squiggly proportionality sign as opposed to an equal sign in the Stefan-Boltzmann relationship, because they don't want to talk about the emissivity factor, which is really quite important as we start talking about strange stars like white dwarfs, neutron stars.
Right.
It actually becomes the key player in interpreting those. But if you don't see it in the equation, and you start to think that it's not an important part of the puzzle, and maybe it's nice to ignore it because of these contradictions as they mount.
Right.
So Pierre, so you just alluded to something like a neutron star and pulse. Over time, they've made measurements and accumulated like assumptions, right? So somebody says, I have a theory about this, and they make an assumption, and then they try to prove it mathematically or observations, and then they sort of accept it, right? And then everybody's incrementally building on it. And the problem is like the weak chain of evidence gets there. The related theory, Unzicker talked about this, which he called subtractive science. And his example was in particle acceleration when they started. They shot a charged particle in a vapor chamber with a magnetic field, and you could measure the curve, and you get some idea about its mass and its charge interaction with the field, which sounds great. And then they started raising the energy of the beams, and then they started making colliders. And the problem was, to see the new thing, they had to subtract out the old thing, right? So they start building sensors that sort of filter out like essentially the noise or the stuff they already know, right? And then the problem is now they're co-designing their sensors with the result,
right?
And at some point they're subtracting out almost all the signal,
right?
And he said the Higgs boson, it was like 2 photons out of a billion that they were measuring, and then the sensor was literally designed to find exactly that photon, and then something stimulated it, and they said, "Yes, I found it,"
right?
Which became circular, and so and you said about the satellite calibration, it became circular. So there's this kind of like the 3 pillars of error is like accumulated assumptions, which may be a little bit wrong or used out of context. Subtractive science, where to see the phenomena you want, you have to design a better and better sensor. And as an engineer, that makes sense. Like if I'm looking for an X-ray photon, I'm not going to make a broad spectrum thing. But now I'm starting to look where the light's good, right? And these phenomena, and then the self-calibration of, well, these assumptions are correct and these assumptions are correct. Then I calibrate it with some confidence, and I make a measurement, but somewhere the chain got broken.
Right.
So you're familiar with the subtractive science problem?
Yeah.
Yeah. So
Actually,
And-
that's what happens in the WMAP satellite and the Planck satellite. Both of them are taking a difference of this. Well, Planck is taking a difference of the sky and a reference load, and WMAP is taking two regions of
And
the
then there's
sky, taking
assumptions
the
about-
difference. Yeah.
So, like, at one point, can you say it goes wrong? Because, like, in particle physics, when they started subtracting out a little bit of signal to get clarity on the new phenomena, like, they were all like, this is great. But at some point, the subtraction got so big that they're essentially just stimulating their sensors. And then between that and calibration, it's the probability of basically finding what you're looking for gets quite high.
Right.
And then, like, but where was the line? Like, how do you, like,
how did it start? Like, when we talked about the white dwarf, why did the white dwarfs become ultra dense? And that's because of basically Eddington, that he knew that the luminosity of a dwarf was low. And so in order to account for the low luminosity of the dwarf, you know, he all he had was Stefan's law, the Stefan-Boltzmann's law. And he had radius squared and temperature to the fourth. And these were the only two terms he had. Well, he had the temperature. He could see the color of the dwarf, so he knew the temperature, at least the vibrational temperature, which we will correct here. So he couldn't touch that term. They dropped the emissivity term, which is Shiloh's point earlier. And so all that was left was the radius. So if the luminosity dropped on the left, so you got luminosity is equal to, I think it's 4 pi r epsilon r squared t to the fourth. And so the epsilon is gone. We assume that there's no emissivity. All the emissivities were 1. And so all that was left that you could change was r. So if the luminosity dropped, for Eddington said, oh, we have to make the radius small. That's how we got a white dwarf. We made it small because we ignored epsilon. And so the only thing that Eddington could change was the radius. So then we made it small. We knew the weight, so we made it ultra dense. Right? When you drop the radius, now all of a sudden they became ultra dense. And then they said, okay, well, now let's look for a proof. Well, the gravitational redshift became the proof. So then when you start looking at the gravitational redshift, the only one that worked was the one for hydrogen. But the problem is there's quasi-hydrogen molecules on white dwarfs, and that will cause a redshift. So you could have a redshift that has nothing to do with gravitation. Then if you look at all the metallic lines, if you look at all the hydrogen lines, let's say the hydrogen alpha line, beta, gamma, they all have different shifts on the dwarf. But if it was gravitational redshift, all the shifts have to be the same, and they're not. Then you look at the metallic lines on the dwarf, and they don't confirm the redshift of the hydrogen alpha line. Some of them are blue shifted, some of them are red shifted, depending on what metal you're looking at. So these are proofs that the white dwarf is simply not ultra dense. It came because Eddington threw away the emissivity, which was Shiloh's point. You cannot throw away the emissivity. And you change the structure. So what happens, sorry, I'll tell you quick. So what happens is you have a certain structure. This is the graphite versus diamond structure, right? I don't know what the structure is on the white dwarf, but I can tell you it's not hexagonal planar. Okay, somehow the structure has changed. The crystal structure of that star is different, and that's why its luminosity is low. It has nothing to do with density, just like diamonds and graphite have essentially the same density. Same with the star, the sun, and the dwarf. The dwarf just has a different crystal structure. So this is a radically different way of reinterpreting the data, and it's high time that it happens. If the sun has a lattice, so does the dwarf. That means it has a different lattice. That's why its luminosity is low.
And I think that Jim's question about, at some point you have to correct for the noise of the observation. You have to start pulling things out, and you're pulling out so much that you're left with something that is a highly artificial picture of what's actually happening.
Yeah, this was the assumption problem of, let's assume emissivity is constant. So now you have less variables to play with.
Right.
And then they were happy to say emissivity is constant. Let's generate a radical new kind of matter.
Sure.
Right.
And that's part of the interaction with astrophysics, which is way out there, and particle physics, who they like to, invent stuff.
Yeah, the problem is
hold on.
But it's not
I want to make a point. I want to make the point, and I think the point is exactly what you said about the hydrogen is redshifted, other things are blue shifted. If you're going to be subtracting away things, in order to verify if you're actually looking at something real, I think you have to have multiple vantage points that all have to agree with each other in order for you to be able to say
this
thing is.
Cherry picking problem. Spectroscopy, every line means something.
Right.
Right. And some of it's well understood, probably some of it's not. But you can't ignore the stuff that's actually well understood.
So they tried to say, even the problem of looking only at the hydrogen alpha line. Okay, they say, oh yeah, we've measured the hydrogen alpha line on Sirius B, which is our closest white dwarf, and we know that redshift is exactly what Einstein would tell us it needs to be. Okay, but the problem is that the other hydrogen lines in the same spectra, they don't want to touch those because they don't give you the same redshifts. So, and the early papers, when they were looking at the redshifts of Sirius B, they started seeing that, oh, well, the hydrogen alpha line has this redshift, and then the beta line has a different redshift, or the gamma line has a different redshift. And so they didn't agree with each other. And then now the metallic lines don't agree. So you just pick the one that you wanted, and I mean, it's just the whole thing is a mess. Well, none of this agrees.
I love something, Jim, that you said a while ago, which is that we're going into this era of AI where right now we have the mapping of simple concepts like words and like single symbols to other symbols. And at some point, we ought to be able to produce a system that actually maps concepts to one another, that allows you to massively increase our computational ability to verify how these systems, how these paradigms, and how these different perspectives on the same thing actually align or don't align. And I think that that's going to be really powerful for science in a way that the systems that we have right now might be less powerful.
Yeah. So it goes to abstraction. So humans think in something I call linear narrative. I see a dog, it's running here, and even equations, most proofs look like this linear set of equations. And since we can't really, we're talking about a white dwarf, which is, some unbelievable number of atoms, unbelievable distance apart, with some amazing number of actual observations, right? So, the solution to that should have been, let's say, 1 million equations with tens of thousands of parameters measured over years. That would be a proper data set. But a human can't do that. They can't do 1 million equations. We can do 10 at a time. And we can't do equations with too many terms. We love to collapse. Right, and we can't take into all it. So
even 10 partial differential equations will have no generalizable solution.
Right. Yeah. So now imagine a system that could actually solve 1 million equations with thousands of parameters and over time. And when you were working on the science, it was always sort of calculating the best fit of that.
Well,
and then you get some error signal, like the error signal you just talked about of looking at the hydrogen alpha line, the error signal on everything else was 100%.
Right.
And you almost couldn't express the idea of just picking this one thing, because if a properly designed system said, take into account everything you possibly can, throwing out a lot of stuff would just be crazy. And it might also help the subtractive problem in particle physics, where the sensors have to get really narrow. Well, if you could actually have lots of wide-ranging sensors, right, even for complex phenomena, and still get a useful signal out of it, then you might partially solve the subtractive engineering problem.
But what's scares, I know so little about AI compared to you. I mean, I'm just a very much of a rookie. But my problem that I have, I'm scared that it'll just build on error. We're feeding these computers human acquired knowledge. And the computers, when you ask the AI a question about the sun, or with ChatGPT, Unziker did that. He had an episode where he asked Chat GPT about the sun and started arguing with Chat GPT. He's an interesting guy to do that. But my question is, how do we get the foundations right that you were talking about earlier in the episode? We don't quite have our foundations right, and the computer's not going to be able to give them to us, right? They have to start somewhere.
Well,
they start from human knowledge, right?
Yeah. Well, they do currently, and that's so. This is a Jim's thesis.
Okay, Jim's thesis. Okay,
feeding language to AI models was the shortcut to seeming intelligence.
Okay,
right. It's not, and then people say we're already giving it everything we can, and we're reaching the limit. Right. So just look around this room. Right. Like the color of that little spot is actually dependent on almost everything here. Right. And if I went in there and I made that spot a slightly different color, would look wrong, because it would in fact be wrong. Right. So physical reality is solving for actual things. Right. And the only way that thing can be exactly the right color is if the laws are working everywhere. And if it was slightly different color, you would see it. Right. So already AI models, if you give it all things humans said, and you lie about some facts, let's say you feed it, 1 trillion sentences, but you put in 20 lies,
right?
They'll stick out.
Okay.
Because they're not consistent with everything else.
Okay.
Right. But they're still human generated. And maybe the whole corpus of human thinking has a bias because how we think. Now, if you start building models that also have a lot of data gathered in a way that it's only consistent. So now the human thinking and the data from physics and sensors, they have to be consistent.
Okay.
Right. Now the problem with sensor data is we don't actually detect reality. We detect photons or electrons that bounce off of reality. Right. And the sensors have their own problems. But if you have a diversity of sensors looking at the same phenomena, there also has to be an inherent consistency because we think reality is consistent. If reality is not magical, it's consistent. So now you have a big AI model that has a lot of very consistent data, right? And then human thinking, which has its biases, so there's errors in it, there's lies, there's biases, there's truth, but it also has a consistency that emerges out of it. And then the combination of those two could potentially be better.
Right.
Now,
could improve. Actually, they might correct the premise.
Right. So then there's what they call adversarial systems. So imagine you say, I have 2 AI models. So humans are computationally intelligent. Like we're not smart because we read a lot of the internet, right? You got very little data put in your head before you got smart. Like it's unbelievably small. But what we do very well is we think about things and come up with a couple of options and then have a test, right? So you could start to say, all right, we have this AI model. Let's vary some possibilities in it and then predict reality in the future. And then from that, design experiments. And then the experiments, if they're good experiments, will say, this is more right than that.
Right.
Right. So imagine doing billions of adversarial experiments. By adversary, I mean there's testably different inputs, which you can see that sometimes it will make testably different outputs, which you then can say which one is a better fit.
Well, it's like at the eye doctor. Is A better or is B better?
Yes. Yeah. And we do this all the time.
Sure.
Like I could give you an argument and say, what do you think? And you say yes or no. That's technically one bit of information.
Because it ends on yes or no?
No, just to say, I think that car is red. And you say no. Right? That's one bit of information. I might have done 10 to the 20th operations in my brain to come up with a hypothesis the car is red. And you falsified it with one bit. Right? So that's how we become smart. Our input data rate, like when kids, start to learn stuff, they try to walk and they fall down. It's a falsifiable event. And then they construct a whole different way of walking and they do it multiple times and pretty soon they're walking pretty well. The number of times they fell might have been 10 or 20. Like it wasn't very many tests of that. But their brains were working like crazy to figure that out. Like little kids' brains are They're pretty excitable. So that's what I mean by computationally intelligent. Like they did a lot of simulating and twitching and stuff, and then did a small number of actual tasks because you don't want to bang your head on the floor 500 times. Like, so we're going to get to the point where, like today, they train robotics with lots of data. Pretty soon we'll have good AI models. We'll load it in a robot and we'll just twitch around and slowly figure out how to sit and walk and stumble a little bit and fall down, and it'll teach itself really fast. So there's a funny thing, which is today's AI models are small compared to human brains. But we make them seem smart by giving them sort of a lot of information. But when the AI models become big, that information is going to get less and less useful, because they'll be better off simulating reality and then testing it than
As opposed to
taking assumptions about reality that were already done. Right?
Interesting.
Does that make sense?
Yeah. So maybe we'll get a better model of the sun from AI, right?
Yes, probably.
Do we have to give it permission to think for itself, like to reconsider the statements of fact that we've fed it? Seems like there's like an unleashing that needs to happen.
There's computers inherently do the next step. So imagine a state machine, and it says, evaluate the current state, and then maybe some output comes in, and then that output becomes part of the current state, and then you just do the next state. So computers don't need permission to make progress.
It seems like a rather rudimentary thing to say, hey, we're trying to develop fusion on Earth. The thing that we see that fuses is the sun. Figure out how the sun does fusion and tell us how to design.
Figure out the sun, or explain these observations, or
like think about it for yourself, because I think that what Unsiker's pointed out with these videos, and sometimes I'll do this just to warm up for lectures. I'll start talking with ChatGPT and trying on like the angle that I'm going to approach this from, and usually at first it will contradict me and be like, no, like we know that the sun, just for example, is a gaseous plasma, blah blah blah, and then you start saying, well, what about this, what about that, and eventually ChatGPT will be like, okay, I see what you're saying, right? So you can kind of twist its arm into...
Yeah, so what's happened, I mean, technically this is pretty easy. Like it's way dumber than you think. So the trained model has a really big state, say 70 billion parameters. And those parameters are essentially the relationships between everything that's been fed, right? And then there's a context window, maybe it's 100 kilobytes. So when you ask it a question which entirely comes out of what it already knows. But the result of your question and what it's decided went in the context, right?
And that doesn't feed back into the bigger pool is the problem, right?
It doesn't retrain the model.
Right.
It's that model training took a month, right? And our brains have a similar phenomena, by the way. So as you build up the context window, it's been designed to prefer the context. So it's sort of inherently agreeable. That's the design choice.
But is there any way to universalize those context experiences such that they can map onto individual users start to overlap their context windows and the thing actually grows?
Yes, that would be very easy.
So it wants to agree with you.
No, it's not so much it wants. It's useful. Say it was designed to help you do like writing or interactive conversation or something. Okay. So the thing that works best today is as you give it context about what you're interested in, it says he's interested in the state of Oregon, not Pennsylvania. He's interested in this kind of politics and not that. It sort of is designed to be agreeable to further your search for something.
I can convince ChatGPT that the sun is a liquid for sure. Yeah. But it will, when another user goes to work that out for themselves, it will know nothing about the fact.
So you could imagine that, somebody serving this model to lots of people could keep all the context and interactions and then train a model with the total of that. But that would just be another human bias on it. So imagine the context window is let's say we want a scientific AI model. So you have this AI model that knows a lot about a lot of things. And then it says, I would like to do these additional measurements. And you do the measurements, and so that's a context, right? And then you generate, what does the AI model think about that context and its current knowledge? keep that in a separate buffer because now this is contingent on. So he says, all right, I sort of learned this. Now let's go do some additional experiments, which may be falsifiable to its solutions, and only ever train stuff back into the model, or maybe never trains. That's really fundamental. So then this goes to a judgment. So now you have multiple AI models. One is taking a lot of its results and training it, and another one isn't. And then as you do new experiments, you go A/B test those guys. And sometimes that fundamental stuff actually expanded the model's like reach. And sometimes it actually was subtly wrong and is actually making it worse. So now imagine 1 trillion of these experiments going on in parallel all the time.
You need a coordination layer.
Yeah, we're good at coordination layers. Like this is complicated, and there's a couple layers of abstraction on it, but it's all in principle doable. It's by today's standards, like the amount of computation to do what I just described. It's like 1 million times the annual, AI computation budget. But that's not that big a problem technically because the universe is energy rich and full of silicon dioxide. Like
Made to compute.
Did I tell you a funny observation? The top 100 kilometers of the Earth is 75% oxygen, silicon, and aluminum.
And that's what you need.
In about exactly the right ratio to make silicon chips. So the Earth couldn't be better designed. No, my theory is the previous race that surrounded the sun created a sphere of computation around the sun because we're about the right distance from the sun to be powered by the sun.
Okay.
So if you make a sphere, 1 millimeter thick around the sun, that would be a very large computer with maximal energy absorption. And then when they figured it out, they took the sphere and made it into a ball.
That was just enough. It was the Solarians that did it.
Just enough carbon in it to reboot the process.
Now, did you know about the Solarians? Did you know? So Herschel. So we go back in the history of the sun. That's why when you brought this up, first generation, first civilization. So Herschel in 1800, he believed that the sun. He was the one that discovered infrared radiation on the sun, but he also believed that the sun was inhabited. He thought the planets were inhabited, I believe, and he thought the sun was inhabited with these beings called Solarians, and they lived on the surface of the sun. But then his problem was that he measured the infrared power coming off the sun, and he realized that his poor Solarians would be cooked if they were really on the sun. So then he invented, this shows a scientific mind, he invented how he was a true astronomer. He decided to solve his problem by putting radiation shields to protect his Solarians from cooking on the sun. So he invented, his radiation was coming from an outer cloud layer, and below that cloud layer, he put his radiation shield, and then below that, then he put his Solarians. So he made sure they weren't cooked. So that was the Solarian model of the sun. So it's not too far from the gas model we have today. I just have to make a joke. So there was an initial civilization according to Herschel.
Sure.
No, I just find it, I don't actually think there was a computational ball around the sun.
No, I know that.
Really funny that the Earth is made out of exactly the right atoms to make computers. So,
right.
Like every once in a while, the universe kind of winks at you a little bit.
More than a little bit, it seems like.
Yeah, it's more than a little.
Hey guys, pardon the interruption. Remember, this podcast is entirely paid for by listeners just like you. If you're already supporting us, thank you. If you are not, please consider you can give 75 cents a week and make sure that we have all of the time in the world to bring you better and better conversations, and we don't have to cave in to nasty advertisers that are going to try to get us to sell crap that we don't care about. So check it out over at patreon.com/DemystifySci. Enjoy the rest of the conversation.
And so in relation to that is this question of electric currents, because I know that in terms of the sun, electricity is important. And when we talk to people that are astrophysicists and cosmologists, currents are kind of electricity is not a major factor of how they model really anything.
Right.
And I know
They don't think about currents, or they also don't think about chemistry really.
exactly.
There is astrochemistry, but they really have very limited stuff on the sun. You know, they try to explain just the reactions that they know that they, you know, if they have calcium hydride, they know, well, somehow I got to mix the calcium with the hydrogen and get that calcium hydride. But they don't really try to think beyond that in terms of condensation reactions on the sun. That's a big difference.
And so earlier you said that the reason that it looks like the corona is at millions of degrees is because you have this, is it fair to call it electrochemistry in the corona?
Yeah, that's what's happening.
Okay, so let's talk about that. Like, why is that important? How does that feature into the sun?
First, we know that the corona has a continuous spectrum. Now, for the astronomers, the way that they try to justify the spectrum of the corona is they say, well, wait, it's actually a photospheric spectrum that has been scattered by relativistic electrons that are causing us to have this continuous spectrum in the corona, okay? Because they don't have condensed matter there, so how do they get a continuous spectrum, right? So they just scatter the photospheric spectrum, and then by scattering it, they can get rid of the Fraunhofer lines, because the photospheric spectrum, you know, if the surface of the sun is emitting a black body, above it there's atoms that are absorbing that radiation, and that gives us the Fraunhofer lines, which are superimposed on that spectrum. So, and also, in order for them to get that black body spectrum in the first place, since they're in a gas, how do they get it? So I had said that we'll get to the electricity eventually, but just so that people are clear, I had said that, look, to get a black body spectrum, you need the vibration of nuclei within a lattice structure. They don't have that in a gas model. So what they do is they, in the sun, for instance, they say, well, most of the continuous spectrum is coming from the negative hydrogen ion, which is hydrogen with 2 electrons on it. And that's highly unstable. I mean, it should not be present at all. And the problem is that if you look at the main sequence of the stars, the temperature changes along the main sequence. So as you go to O-class stars, you still get the continuous spectrum. But now you can't use that negative hydrogen ion to explain it. So now they have to have a different agency to explain that spectrum. So how do they get the spectrum on the sun? Now, it was Wilt and Chandrasekhar that said that you had negative hydrogen ion in the at the level of the photosphere, which is causing the continuous spectrum. But that's not sufficient. They need other processes. So that's what the stellar opacity project was. I think it was at Los Alamos, where they took a whole bunch of processes that had nothing to do with thermal radiation, and then they just sum them together and say, oh, with all these processes summed, we can get a black body spectrum. But the problem is none of those individual processes occurred at the same temperatures, right? They're looking at transitions, like bound transitions within atoms or something like that. And then they're putting them all together to give me this soup, which eventually gives the black body spectrum. And what I say is, no, the sun has to be like, it has to behave like we get a black body spectrum on Earth. It has to be done instantly, not by the summation of all these processes that are unrelated. So you get this black body spectrum from the surface of the sun, which will come eventually. Science will move to a condensed matter to explain this. But there's atoms above, there's neutral atoms above the surface of the sun, and they absorb some of that black body radiation, so that's why you get the Fraunhofer spectrum of the sun. Now, in the corona, well, they don't have all these processes to build the continuous spectrum. They see it, but now they don't have, you know, the negative hydrogen ion and all the things, all the soup that they had internally to the sun to give the continuous spectrum. So what they say is, oh, well, the way we get that spectrum is by taking the continuous spectrum of the sun with the Fraunhofer lines, but now we have relativistic electrons, and those relativistic electrons are scattering the spectrum and getting rid of the Fraunhofer lines, most of the Fraunhofer lines, and that's now why we have the coronal spectrum, which is continuous, but it's not really a property of the corona. It's a property of the photosphere. I mean, this is just the height of absurdity.
Fairly intelligent scattering, because it's scattering things in just the right amount to give you the spectrum and the other thing. And it's just Occam's razor says it's
it's just so what I'm saying is that there was at the eclipse of 1869, I think, in Iowa. It's a long time ago. And I can't remember the name of the man who said it in the paper, but he said that the corona was self-luminous. In 1869, somebody said it was self-luminous. He saw the continuous spectrum and he said it's self-luminous. Okay, but astronomy moved away from being self-luminous, right? They're now scattering photospheric light, and I'm saying no, it is self-luminous. You see the streamers in the corona. We have structure there. Okay, it's not relativistic electrons. It's self-luminous, and what's more, the coronal spectrum reddens as you move away from the surface, so it's cooling. Well, this shouldn't be happening if you're just scattering the light of the photosphere, right? Why is the spectrum of the sun reddening as you move away from the surface? So this speaks to the temperature. The temperature is lower as you move away, okay? But the current theory says we're at millions of degrees. And this gets back to now electrochemistry. Why are we getting millions of degrees? And what I'm saying is you have in the corona, you have condensed material, and it's linked all the way down to the surface of the sun. So you can see that actually, if you take an iron-13 spectrum of the sun, you'll see that iron-13 there's iron-13 very close to the center, to the sun, to the surface, and all the way out in the corona, right? You can see the iron-13 all the way, right? So what's happening is you have charged material. It's electropositive. So the corona got some, it's plasma, it's mostly plasma, but there is some condensed matter in it. And what that condensed matter is doing is it's electropositive, and it's bringing charge from the outside of the corona. If you have a neutral atom like iron, it now touches this highly electropositive material, and then it loses its electrons. And the electrons are now channeled back to the surface of the sun. And when this becomes equivalent to a condensation reaction, there's going to be heat involved. And to get rid of the heat, the iron promotes one of its remaining electron, and then that emits light, and that gets rid of the heat. So that's the emission line that we see. It's a sign of a condensation process. So that's why the lines are emitting. They're giving away their electrons and they're emitting light.
Why is there this electropositive material there?
Why is it there?
Yeah.
I'm not sure why it is that it's there, but if you look at the formation of how would we form a star, in one of the ways you could form a star is with hydrogen clusters. And so so in the modern theory of the sun, you eventually get to your question, but we'll start at why could the sun naturally be positive, have positive charge? So in the modern theory of solar formation, you have a cloud and it self-gravitates. That's the modern theory, right? In the standard model of the sun, you have a nebular cloud and it self-gravitates and forms a star. It's kind of like the hands of God came and pushed this gas together, right? But the problem is that gases don't self-compress. Okay, that doesn't happen. And when you cause a gas to gravitationally collapse, like they require in astronomy, and I was telling this to Jim yesterday, you actually generate negative heat capacity. So that the gas will, as it loses light, as it emits light, it actually becomes hotter. So the temperature goes up as it emits photons. So it's got negative heat capacity. Whereas normally a gas has positive capacity. If it emits light, it cools. So what's happening is that all gases...
Sorry, I didn't follow. Is that some feature of compression, or like why is that?
No, it's because their models are wrong. Gases, so gases all gases that we have on Earth, they all have positive heat capacity. But in astronomy, because they cause the gas to self-gravitate, when they did that, they made the heat capacity negative.
Got it.
They got it in their mathematics. The heat capacity became negative, and they said, oh yeah, stars will actually heat as they age. So Eddington actually writes in his book, I don't know how we're going to get out of this. How are we going to get out of this vicious cycle that as the star starts condensing on itself, okay, the temperature is going to go up as it's radiating away heat. How are we going to get out of this? And what ends up happening is they solve it with a Nobel Prize. They give a Nobel Prize to Chandrasekhar for degenerate matter, right? So what happens is the star compresses itself and eventually you get a degenerate object and that stops the compression. So that's why they want the white dwarf theory, because that also solves their negative heat capacity for the sun. So all these things are related problems. They're not independent. They created a monster and then they solved it by giving us degenerate matter in the stars.
It's also observationally contraindicated, right? Because these giant nebular clouds are actually not gravitationally bound, and increasingly evident that that's not the case.
Right. And that's correct. They actually have seen expansions in some of these clouds, so it's not working. So gases expand. They expand to fill the void, and so this just doesn't work, and that's their mathematics doesn't work. So what happens? So if it's not gravitational collapse, how do you build a star? So the idea
but it's fairly easy to calculate. If you take a gas, right, and you say, all right, here's a gas that's like the mass of the sun and it's some big space, and then it has a temperature and energy. If you say, what's the odds of it collapsing? Well, the gravitational field of any piece of the gas falls off so fast, it doesn't counteract its natural tendency to disperse just by random thermal motion.
Right.
And it's not a hard calculation to make.
Right.
Like there's just nothing to it.
You can pop a huge balloon in space and it will.
Yeah. So then the counter theory is, there's a big gas and something like a shock wave from a supernova causes some movement in the gas to sort of trigger the condensing event. But it's not obvious what
James Jeans went even further, right? In the idea that that you make a star from gravitational collapse, James Jeans actually invoked that I can't remember if it was photons or whatever coming out from the outside and then containing this thing and slowly making it into a self-compression. But anyhow, now that so if it's not self-compression, what is it? So what I say is, if you look at cluster chemistry, and so I'm an inorganic chemist, you look at how does hydrogen actually, some people think, well, hydrogen is just diatomic. Two hydrogen atoms come together and that's it. It doesn't grow anymore. That's not correct. If you add a proton, you'll get H3 plus. And if you add, then you can add another, maybe a hydrogen atom to it, and it just keeps growing. Okay, and you can keep building, as long as you have positive charge with it, you can keep building larger and larger clusters. So we have clusters of hydrogen now that are more than 100 atoms together that's been built in the laboratory. And so what happens is that you get these hydrogens come together and now you've delocalized the electrons within this cluster. That's how they're sticking together. You're starting to delocalize the electrons. They're starting to share electrons. So what I'm saying is a star actually starts by a very simple process, one atom at a time, that you have hydrogen, you have it coming together, and then there's a positive charge that comes. And so eventually you build up this cluster larger and larger, and in the end, it's positive. So then when you have a star, where are you going to put this positive charge? And what I'm saying is the positive charge is moved out into the corona. Okay, the star at the surface of the sun, we know that it's neutral. Above the granules, it's neutral. There's lots of neutrals there. That's also my argument against the negative hydrogen ion, by the way. Why don't we see fluoride or chloride? We don't see them. So if you don't see those, and we know we know there's hydrogen chloride in sunspots, we've seen it. So if there is chloride and fluoride, Okay, hydrogen chloride, hydrogen fluoride. You never see them as free ions. You only see the molecules. Okay, so if that's true, if you can't even see chloride or fluoride, how are you going to get hydrogen anion? Okay, so it just doesn't make sense.
Is there any hope of seeing these little droplets, these primordial starlets?
I don't know what is hope. I mean, they're pretty far away. And how are we going to detect them? Sometimes maybe by spectroscopy you could see them, but I don't know what the spectroscopic signature would look like. Maybe we've already seen it.
If we can already make it in the lab clusters of 100,
right?
Is there a way to stimulate it with the ambient radiation of the galaxy and then see if it has absorption?
Yeah, well, maybe there is.
Like that's a nice.
Yeah, maybe
that's a very engineering.
And this could be my ignorance of. Yeah. Somebody might be listening to the video and say, "Oh, well, Pierre, here's the spectrum of H83." You know. H83 plus or something like that it exists, and that's a spectrum. I've never seen the spectra, so I can't say what the spectrum would look like.
What induces hydrogen to start to bond in that way? Like if you have a gas cluster.
It's a sharing of charge, right? You've got a proton and it's looking for electrons, and it comes and just shares the electrons that are available. So it's all about delocalizing electrons over lots of atoms, and that's just how metallic hydrogen is. It's sharing its electrons. And also Neil Ashcroft, who had written to me, he was probably the top person in the theory of metallic hydrogen in this country. And when I wrote the 40 proofs paper, and I talked about this in a previous video, but when I wrote the 40 proofs paper, people were upset because I emailed the scientists of the world, you know, like I got a list of all the world's physics departments. And then my sons and a whole bunch of people got together, and we emailed like 70,000 people.
That's incredible.
Here's the 40 proofs paper. So physicists cannot say that they don't know about the 40 proofs paper, because I emailed it to 70,000 physicists around the world.
Check your inbox. I
check my inbox. Check your inbox. And of course, I've been attacked for this, but John Wilkins, who is like one of the best physicists in the country, he actually said, you know, I'm thinking when I first did I did it for two papers, the WMAP paper, WMAP or radiological analysis, and the 40 proofs paper. And when I did the WMAP or radiological analysis paper, John was having, he'd come over for Thanksgiving and Christmas. So that Thanksgiving, we were emailing the WMAP paper around the world. It also got over 60,000 deliveries to physics departments around the world. And so I asked John what he thought, and he goes, well, I guess there's nothing wrong with sending a polite email. And you should know that Raman, who had won the Nobel Prize for Raman spectroscopy, when he discovered Raman spectroscopy, he got a secretary to send letters around the world of the discovery. And then some Russians got his letter. They were working on the same experiment, but they saw that Raman had just finished publishing it. Okay, so it is okay. You know, now people didn't like my methods, but here's what John said, right? I guess it's okay to send a brief email, you know, to everyone. So that Monday, so that was Thanksgiving. John goes to work on Monday, and an astronomer that knows him well, he was furious to have gotten, I had just finished emailing OSU, and he was just furious to get the WMAP paper and talk to John about it, that, you know, Robitaille sent me this WMAP paper and blah, blah, blah. And John just goes to him, he said, John told me what he told me. He said, well, did you read it? Did you take the time to read it? Mm-hmm. And so the WMAP paper, some people did clearly read it. I got a lot of response back. And the 40 proofs paper, the same thing. It was downloaded tens of thousands of times from the server of Progress in Physics, because Dimitri would keep the downloads and tell me, you know. So I know they downloaded it. So anyhow, so now what was the question that caused me to talk about this? It was, why is it positive? So you can see that now it grew as a positive entity. And now what I'm saying, it's like a Van de Graaff. The sun has a corona, and it's sending those charges out away from the surface, and the surface is surrounded by neutrals. Okay, so I think everything fits that it's pushed now these charges out. Once it made metallic hydrogen, it pushed the charges out. And so we want to have it electron rich. The sun is more electron rich. It could be totally very close to neutral, with positive charges on the outside. I don't know if
this is where you do the math, because the sun is so big.
Yeah.
Right? And it could be mostly neutral. And then conductors are really cool because they put all the excess charge, positive or negative, on the outside.
Right.
Which can create a very high field.
Right.
Because the charges are pushing away, even though 99.99% of the matter is neutral, you can still have a very high field. And the very high fields interact with atoms in really cool ways, like pulling off electrons and creating lots of spectroscopy. I can't say that word.
Can you tell people about the back of the envelope calculation you were doing about the motion through the galaxy?
Yeah, well, so the published literature now says there's really strong magnetic fields in the galaxy. And magnetic fields cause charged particles to move, and some percentage of the interstellar mass is ionized. And so that says things are going to move around, right? So, and the really nice thing about magnetic fields, I guess, it polarizes light, so you can like observe what the field strength is, even though you're far away. So that's magical. Like it's like I can't even believe it. So then there's the theories about the stars going around the center of the galaxy are going too fast as you go out in the electric universe. Guys say that's because there's a big magnetic field and a big current, and that's moving things around. And I thought, well, if I take Google the magnetic field strength to the center of the galaxy, and the sun was charged, how much charge would it be to accelerate a charged mass in a circle, ignoring gravity? Like, it's a simple calculation. And the density of charge in the sun was really low. Like farads per kilogram. Like, it's a couple of extra electrons. And like the sun could have a net charge. If the sun has a net charge, it doesn't have to be very big, because the weird thing is electromagnetic fields are 10 to the 39 stronger than gravity. So charge likes to bounce, and the universe seems to be equal positive and negative charges. But charges also like to move, right? And, the plasma in space is non-collisional, and there's big magnetic fields, which means it's going to move. And since it's non-collisional, there's no resistance. This is a really weird thing. So the plasma moving around the universe is essentially a superconductor, because nothing slows it down, right? And everything that has no R, no resistance, electrical engineering term, all circuits are capacitor, inductors, and resistors. If R is 0, then the energy will slosh back and forth naturally. Like, it literally turns everything into an oscillator. So you could have a big magnetic field in the galaxy, and it goes one way for a while, and then it goes the other way for a while. And you say, why? Well, you just calculate the resonance frequency of the galaxy, and that's what it will do. And apparently there is a undulating magnetic field.
Right, that's what Ben Davidson talks about, is that the galaxy is about to go through and reverse its magnetic field.
Yeah. And so these fields are really strong. And then you made the point of the local detail of the magnetic field is very complicated. And that's, magnetic fields sort of self-organize into bigger and bigger shapes. But it's sort of like a turbulent flow, where the flow, if you look at a fine part of a turbulent flow, it looks like all turbulence. You can't tell which way it's going. But the main flow is actually still moving. And so and yet again, these calculations aren't hard to do. Now, like whether it's true or not, well, you'd want to know what's the charge of the sun, which maybe we could figure out. And they're figuring out what's the magnetic field map of the galaxy, which is kind of amazing. And we know what percentage of the interstellar gas is ionized, which is amazing. And ionized particles react actively with electromagnetic fields, whereas neutral particles, not so much. But if it's dense enough to be collisional, ions move neutral particles.
And so the charge on the surface of the sun in this model would be the thing that propels it to orbit?
It's possible. Well, if it has a net charge, it'll be affected by the magnetic field. It has to be.
Interesting.
And that's really simple equations. Too simple to be honest.
All our EU listeners just jumped up and started cheering.
I know.
But I don't know if it does have an S charge. I mean, it's a beautiful calculation, easy to do.
Well, if it's positive on the outside,
yeah.
So either it's neutral and
Right.
it's separated charge,
Right.
or
That's the thing we
it's
don't-
net positive and the net charge is on the
Right.
outside of the conductor. Like those are
Yeah,
two,
those are the two possibilities.
yeah.
Well,
And they're both interesting hypotheses.
but if there's enough positive charge in the corona to produce these electrochemical effects, then and there's no negative charge on the surface,
Right.
then doesn't it make the outside of it positive by
Right. It makes it look like the sun has a net positive charge.
Which case it would be affected by dynamic fields. And then if you know the charge, you know the force, and like that's a really interesting thing. And then so the other thing about the, I guess it's Alfvén and Pratt and all the plasma physics guys, they see the magnetic fields and they see mass in filaments, either wrapping around, like there's complicated, like it's so complicated that it's unbelievable. But you can see the filaments both in the galaxy and between galaxies
By the way,
of charge.
Tony Perrott, when I published the New York Times article, he's the one that asked me to send my paper on Kirchoff's law to transactions in plasma science, IEEE transactions in plasma science. Tony called me and he said, I want 2 papers from you, one on Kirchoff and one on the sun. And it turns out that by the time he asked me in the New York Times article, I had said that you could see that I believed Kirchoff was right. But by the time Tony asked me, I had already come to the realization that, oh my gosh, no, it's all theoretical. Kirchoff is wrong. Kirchoff's law is not correct. So that paper in 2003 in IEEE is the first paper where I clearly say Kirchoff's law is invalid. It takes the vibration of atoms in a lattice field to get a black body spectrum. And then, so that was one thing I wanted to mention. The other thing I wanted to mention, when we were talking about the sun, just recently somebody asked me people have been asking me about the formation of planets. And I had never really, I spoke about it just briefly in one of my papers. I talk about how intercalate regions will be important in the formation of the planets, and I don't go beyond it. But last week, I guess it was last week, when was I in Colorado? 2 weekends ago, not this last Sunday, but previously. And I gave a talk there, and that for the first time I talked about formation of planets. So remember that in my model, in the chromosphere of the sun, you see condensation reactions. That's why the lines are in emission. And I say, if you see emission lines in astrophysics, you're seeing condensation reactions. So the first stars become extremely hot. So I look at Wolf-Rayet stars. Astronomy considers Wolf-Rayet stars the oldest stars, except for Anne Underhill. She thought that they were young. And so Wolf-Rayet stars don't have lattice structure. They don't have that continuous spectrum, so they don't appear on the HR diagram. They are so hot, they don't have an organized lattice. But they're still condensing, so they have emission lines, extremely powerful emission lines, which in the modern model, in the standard model, they say, well, those emission lines come from stellar winds that are pushing material away from the star, because they have no means of creating the emission lines. I say, no, that's not what's happening. That on the Wolf-Rayet star, you have emission lines because you are condensing still. So you have hydrogen and helium emission lines as hydrogen is being added to this star. That's why you have emission lines. Then what happens is the Wolf-Rayet star then evolves to a luminous blue variable. The luminous blue variable is now oscillating between having a lattice, it can have a thermal spectrum, or having very weak emissions. So what's happening? The star is trying to form a lattice, but as it does, it becomes unstable because things are emissible. So in the luminous blue variables, we know that they're extremely active stars. They expel material. So that's how I'm saying the planets were made. When the sun was going through its luminous blue variable stage, it had high angular momentum, and then it expelled the first planets like Jupiter and Saturn. These planets were the first ones to be expelled. And that also means that they could have been, their metallic hydrogen could have been made first in the sun, and then it came out of the sun and made those planets. And then why does Uranus have a tilt? You know, its inclination, it's in the ecliptic plane, but its tilt is almost, I think it's 97 degrees. It's almost in the plane. The rotation of the planet is in the plane of the ecliptic. Almost in the plane of the ecliptic. So what could have happened is when it came by the other planets, it interacted with them, and that caused the tilt to change. So then I was telling this idea to Steve, and Steve goes, well, you know, Pluto is outside of the ecliptic. Maybe it didn't come out of the sun. It could have been a captured planet. So Pluto could have been expelled, for instance. But then I told Steve, well, maybe Pluto was expelled from one of the large giant planets, and that's why it's out of the ecliptic, because like Saturn is tilted a little bit. Its tilt is, you know, in such that it could have put Pluto out of the ecliptic, or maybe that's why Mercury is out of the ecliptic too. Those are the two planets that are out of the ecliptic plane by a significant amount. So maybe they didn't come out of the sun.
Speaking of capture, like under your model, the stars don't, you know, all go nova, right? They cool off, and as they cool off, wouldn't they end up looking a lot like a Jupiter or a Saturn after?
They end up, well, what I say is the stars are moving, as they move down the main sequence, they're slowly cooling. So most stars are along the main sequence. So that's what we want. We just want them to stay along the main sequence and just slowly cool and become a red dwarf.
But if you extend that main sequence long enough, you actually can get to the spectrum of Jupiter.
Right. You get to objects that have very, very high molecular characteristics. They're very rich in molecules at the end of the main sequence when you get to M-class stars and so on. So they're cooling, and then so they're staying along the main sequence. And then you have unstable stars. So when I talk about the sun, I say, okay, it has the intercalate zones inside of it, and when the intercalate zones expand, that explains why we get a red giant, right? That you get, it's like the piece of graphite that if you take a piece of graphite, and I mentioned this to Shiloh yesterday, if you take a piece of graphite and you put it on a table and it's 1 centimeter thick and you saturate it, you make it super saturated with a gas. And then you strike the table with a hammer, it'll expand 100-fold. So if a star has intercalate regions within it, so you have a hexagonal planar hydrogen layer, and then you have an intercalate region. Well, now if something comes and shocks that star, then that can cause the intercalate region to go from solid phase into gas phase, and the whole thing will explode, either as a supernova or slowly explode and become a giant. And that could explain why stars are repeatedly going nova. There's several stars that have repeated nova.
That's wild.
Yeah. So the intercalate zone, when I talk about this model of the sun, it's not just that it well explains the emission of the sun, that we get the thermal spectrum properly, but it explains other star types, because the intercalate region, once you form it, you can now automatically explain both red giants and supernova very elegantly without coming out with some new wild idea. These things fit into known inorganic chemistry.
So where are all these dead stars at?
What do you mean the dead stars?
So if they're cooling off the main sequence, you know.
Well, I don't know how old the universe is.
Well, that's what I'm saying. So if the Big Bang turns out to be not 14 billion years ago.
Yeah, like now we're at 26.
Even if we jump to
27.
Okay, whatever we're up to, right? Let's say it keeps getting longer and longer. Let's not even say that the universe is eternal, but let's just say it was a long time ago, the birth of the universe. Shouldn't we have a huge zoo of Jupiter-ish looking dark stars?
Maybe we do have such objects and we just can't detect them. They're so cool. I don't know if they're there or not. They'd be far away from our sun. So how do we detect them? So I'm not saying that they're absent. I don't know that there's evidence that they're present yet.
Or is it possible that they're right here with us and we just don't recognize them?
Right here.
But what do you mean by right here?
Well, like Jupiter or Saturn.
Oh no, I don't think that the stars. I think that Jupiter and Saturn, all our planets, because they're in the ecliptic, I think they were emitted from the sun.
It's funny because we talked to this astronomer at
Sean
Florida.
Raymond.
So Sean does these simulations, and we kind of pressed him on this because that is often the response is that, well, no, even if you had all the time in the world, sure, maybe these dead stars would look like Jupiter, but we couldn't get them in the ecliptic. And so he actually ran these simulations, and he determined that it actually was possible that a passing body like Jupiter could get captured into the ecliptic, but that it was extremely unlikely. Right.
Well, the problem is,
Yeah,
I mean, you
because
look
then
at
you
the
have
distance to the nearest star.
But given something, I'm not even going to say given eternity. I'm going to go with given a great deal of time.
But why do you want to capture the star, the planet, when you could just form it by ejecting it as the luminous blue variables do?
Well,
we have evidence that the luminous blue variables are ejecting material. And when you eject Jupiter, remember that most of the angular momentum of the solar system is in Jupiter and Saturn. So when the stars were made, they had high angular momentum. And how are they getting rid of that momentum? They eject the planets. So that also solves the angular momentum problem. Whereas capturing Jupiter and Saturn doesn't solve your angular momentum problem of the central star.
Makes it worse.
It makes it much worse. So now,
so they bring a lot of angular momentum to the table if they're captured?
No, but the problem is that it's thought that stars. So in modern theory, when you form a star through this gravitational collapse, they try to figure out how are we going to get rid of the angular momentum, and they do that with solar winds or magnetic fields to try to get rid of the angular momentum of the central star. Mm-hmm. Now in this model, I'm getting rid of the angular momentum very nicely by ejecting the planets in the ecliptic plane from the central star.
I think you just predicted the mass of the planets in a stellar system, right? Because if you know the mass of the star and you think you know its rotation rate, then you know the mass of the planets there. That slowed you know what the angular momentum of the star would have been.
Well, we know that the sun currently has about 4%. So it depends how you calculate it. If the sun is homogeneous throughout, it has about 4% of the angular momentum of the solar system. But most of the angular momentum is sitting in Jupiter. I think it's got about 60% of the angular momentum of the solar system.
Something that I haven't totally understood.
Of course, that one's orbital and the other one is spin angular momentum.
That's what I was going to ask.
Okay, so
the axis is really big.
Yeah.
It's like the old force times.
So for Jupiter, we're talking about orbital angular momentum. So we had spin angular momentum, and it was converted into orbital angular momentum in the planets.
Got it.
Okay, but if you look at the total angular momentum of the solar system, the sun is about 4% if you assume that the sun is relatively homogeneous. If you assume the standard model of the sun, where they put all the mass at the center, most of the mass at the center, because they have a very high density at the center, then it's only about 0.3% of the angular momentum of the solar system.
Wow.
But so what I'm saying about this new model is it does enable us to account, because I'm looking at how were the stars formed when we started making a lattice. The luminous blue variable became unstable, right? And so it emitted the initial lattice. As it cooled, it's starting to form a lattice, and it's emitting them as planets. And then after that, it cools itself more and more. As it loses angular momentum, it doesn't have the ability to kick out more material. So the star, our sun, as it started forming a lattice, it initially gets rid of a lot of its angular momentum with the gas giants, and it cools more and more, and then it has less angular momentum to get rid of. But now it does it with more evolved planets, which are the central planets. The sun is making those elements more and more complex, and now the central planets, like our planet, has much more evolved atoms on it. So I think it fits very nicely, but of course people can criticize the idea and think about it.
Do you think that like the Earth and Venus were ejected as is, or do you think they were more of a gassy ball, but they're close enough to the sun that subsequent, mini eruptions blew the gas off?
So I don't have all the explanations of how they were emitted in terms of time, but it's likely that, the Earth and the Moon could have been emitted simultaneously, that very close in time, so essentially simultaneously. So that it's not something that came and hit the Earth and made the Moon, and that they came out simultaneously.
That seems like a Justo story.
There's some really interesting movements in planetary science right now concerning the evolution of Neptune's two super Earth-like planets, and of course the Earth being a smaller version of something like that. And so I do see people in that field starting to entertain the idea that planets evolve from one sort into another, given proper conditions. And of course, you can accelerate that by moving the giant closer to the star and rapidly photoevaporating its surface and things like this. But it seems like it's at least a potential solution to the distribution of these planets inside of a lot of these exoplanetary systems that we're observing.
Well, I don't know that there are a bunch of exoplanetary systems, by the way. So remember that how are they detecting all these exoplanets? I mean,
differently.
There's several ways, but one of the most prominent ways is always a change in luminosity of the central star. They don't see the planet, they just see that the central star is oscillating in its luminosity. And I'm saying, no, that oscillation is coming because the star is oscillating between one lattice type and another, and so it changes its luminosity. So there's actually no planet. That's why you get these, to me, absurd numbers where you get a planet or two stars orbiting one another in 4 hours, or a few hours for a planet to go around the sun, around its central star. And what is more likely to happen is that you have a phenomenon going on the surface of the star where it's oscillating between one lattice type and another. So it's on the phase diagram that you have, pressure on one axis and temperature on the other, and you're just moving up and down along a line where the temperature is changing, but the pressures aren't changing. But when you go from one temperature to another, you're changing lattice, and that changes the emissivity. So now we get back to this point of emissivity not being present in the seven.
Boy, we were a real dud at a party recently because people kept coming up to us and asking us what we thought about the discovery of life on this exoplanet. And your video, I don't know if it was a conversation or a video I watched of you, but your idea was fresh in our mind, and we had to be like, well, they might not have even seen a planet at all.
I love when they discover planets. They always have a really good picture.
Oh, yeah.
It's like the same resolution as the picture of Jupiter, which is amazing. And
all these exoplanets are all large. They're all Jupiter-sized planets because they need that, because remember, they need to occult a star. So they have to have a pretty big planet going around. It's overreach. Now that it's overreach when you look at the luminosity of the star. Now, there's another way to detect planets, and that's looking at the spectra. You're looking at spectra, and that's more complicated, and I have to look at it more carefully and see, okay, are we actually seeing a planet? Because remember that the spectra of a star can change as well if you change the underlying crystal structure of the photosphere itself. That could affect what you're seeing above that photosphere, because these things are linked.
Well, there's a few that we see from the top down, right? So
there's some that we see visual. There's actual visual observation of exoplanets, and they move slowly. I mean, it takes years for the planet to go around the star. These are not spinning tremendously fast, and so the exoplanets that we've seen optically, those are moving slowly, like we'd expect,
because the plane is perpendicular to us.
Yeah,
and then they just see them,
and we see the planet rotating.
Like I've seen photo or images where it's the protostellar disk, or like the sun still has like a large disk and there's lines that are etched into it also.
Now, now you hit a sore point for me. So this is an example.
Like a little filter refinement.
So this is the problem with astronomy, right? They want to see protoplanet. They want to see a protoplanetary disk.
That's right, yeah.
Okay, so they see a disk around a star and they say that's protoplanetary. Well, how do they know it's protoplanetary? It could be that the star ejected that disk.
Well, it's got lines in it. It's got lines in it.
It's got lines in it. That's fine, but it doesn't mean that it's part of how the planets were made. Yeah. The star could have just created this disk itself by ejecting material from its equator and into its ecliptic plane. So my problem is, if you look at our own solar system, right, we have an asteroid belt between Mars and Jupiter. And I talked about this 2 weeks ago, there was a person at the Naval Observatory, he's deceased now, his name was Tom Van Flandern. And Tom, the one thing I'll say about him is he had the most beautiful blue eyes I can remember. But Tom, he was
so sweet.
I just will always remember this man's blue eyes. He was just, he had great blue eyes. And so Tom believed that the asteroid belt came because a planet was once there. Because if you look at the Titus-Bode law, the planets occur according to this law. We know all the way out to Uranus that they follow the Titus-Bode law for the distribution of the planets.
It's like
right where Sirius is, which is an asteroid in the asteroid belt, that's the proper position for a planet to have once existed. And Tom Van Flandern actually stated that there was a planet there once and it exploded. And that created the asteroid belt. And most of the material of the planet is now gone. Now, even the astronomers say that 99% of the material that was once in the asteroid belt is now gone. Okay, that's their own belief. So why do we have an asteroid belt there if the planets are formed by protoplanetary mechanisms? I mean, why isn't the asteroid belt accreting all its matter and forming a planet? It doesn't. It never will, because you've got, when they treat the angular momentum of the solar system, they treat it as solid body rotation. Well, a solid body rotation, how is this piece of material going to catch the piece in front of it if they're both rotating as solid bodies? It doesn't work. And actually, Steve right now is writing a paper against all this accretion stuff in astronomy, that there's violations of thermodynamics right and left in the accretion mathematics, that they make temperature non-intensive and so on. So there's some real problems there.
You can't get pebbles to stick together either, it turns out. Yeah, so you can get grains of sand to stick together, but pebbles just bounce off each other.
Well, then some of the asteroids are so cool because it looks like there's two balls stuck together. And the shapes are really complicated.
So anyhow,
I don't think there's explanations for that, actually.
Well, there's another problem too. Some of those asteroids, like Ceres, you mentioned in Vesta, they're too rounded to actually be in this hydrodynamic equilibrium necessary to round a body out. Like we were talking about, the sun is almost perfectly round, and they have this hydrodynamic explanation for why that's the case. But you can't actually apply that to some of these asteroids. You don't have enough mass to pull it off. And so, well, how did they get so round? Could they have been?
They bump into each other.
Like a rock tumbler.
It's a rock tumbler.
Gem tumbler.
It's an asteroidal rock tumbler.
Okay.
I think that rock tumblers get you smooth, but I don't necessarily know that they get you round. Do they?
Yeah.
I guess maybe long enough. River rocks are very round.
Yeah, they're kind of rounded.
Over long time.
It's kind of wild. Well, river rocks are another mystery. Like, what are the river rocks doing at the top of the mountains?
That's one of my favorite topics recently.
Yeah, it's really fun. Well, but on the observation, you pointed out that the black hole picture was 6 pixels. at 100 megahertz.
Pierre,
You pointed that out.
Yeah.
And then somebody said, it's amazing that the picture looked just like the black hole in
Yeah.
Interstellar, which is hilarious because they asked the physicists what it should look like, and then they made an image, and then they recreated the black hole that looked like. And
It was
it's
just
so
that image was just disaster. I mean, they had like 5 points, and they took a Fourier transform on 5 points. It's like, okay, only in your mind can you do this and get me an image. So I wrote several. There's several videos that I did on the
like it's so
on
great.
the black hole image. And I was attacked when I did it. And then finally, a group of Japanese scientists, they wrote a paper saying, yeah, basically agreeing with me. You don't have enough data here to get that image.
That is the most heartbreaking lecture that I do at the university. Like, I think that's when all the students turn on me, pretty much.
You're like, they
you
want the
can't
black
take
hole.
the black hole from us.
Yeah.
No.
I mean, the black hole temperature from Hawking, I mean, that temperature is non-intensive, right? So temperature needs to be intensive. That means when you measure it, you can't do thermodynamics if temperature is not intensive. You have to be able to measure temperature at every point. And so in Hawking's temperature equation, which he has on his tombstone, is if you take the black hole and you cut it in half, the temperature increases. It doubles. Okay, well, this is nonsense. If you have a brick and you cut it in half, and you could do it magically without putting heat into it, the two halves, or a cake, let's take a cake and you cut it in half, the temperature of the cake doesn't double. So that's why temperature is intensive. You know, it doesn't matter how the geometry of the system changes. You know, the volume, you can half the volume, that's an extensive property. You half the volume, that's fine. And it'll halve, but the temperature will stay the same. And so in Hawking's equation, it doesn't. And also their entropy of the entropy of a black hole is not extensive. It needs to be extensive. Entropy is extensive. Now, of course, Boltzmann was very smart. I mean, I'm amazed by this guy because he realized that his entropy would not be extensive if he didn't have enough atoms. So he knew that he had to have a certain amount of atoms. I think it was about 1,000 or so, but he understood that his expression would not become extensive if he didn't have enough atoms.
What do you do when you've carved...
When you're a genius like Boltzmann?
Well, no, when you've carved these equations into someone's tombstone, like, how does the civilization as a whole, with this impressive scientific apparatus that has given us so much, how do people save face and move on from these kind of errors?
Well, I don't know. I mean...
So, like in business, companies go bankrupt, right? So you get good at doing something. Like companies all go through a cycle. Like you kind of wander around, you figure stuff up, you ramp, it's called the S-curve. And then you go into production mode, and then the world changes, or you lose the plot or get bureaucratic, and at some point you fail, right? And then companies, like there's a famous tech company called Cisco, so they have lots of product lines. But periodically, when there's a new thing happening, they do what's called a spin out or a spin in. They invest in a new company to make the product, and if it's successful, they have a pre-agreed deal to go buy it, which depends on the terms. So that gives a fresh start, because when you start an engineering project with one person, right, you don't have any priors. Like usually you hire some experienced people and skilled people, but there's also a thing where if a startup starts by hiring everybody from the old place, they'll just reproduce the old culture and methodology. And so in a healthy business world, companies are constantly being created and destroyed. And one thing I think is sad about the modern world, where big companies buy other big companies, because they're trying to get a monopoly advantage, not an innovation advantage.
Is there a parallel that you can imagine for the acquisition of basic knowledge about the universe?
Well, imagine you said, we're going to create a science institution, and we're going to do, I think of zero-day science. Like, let's take all the data and have a culture which, if somebody says, well, I know Kirchoff's law is true, you go, no, you don't know that. Like, how do you go? We have so much more data now, and so much better collected than 1800s. And if you started reanalyzing all that, would you come up with the same
I
electromagnetic
think,
field theory?
it's a strange thing about science. We have no courts.
Yeah.
Right?
Yeah. But how do we-
And because we're not basketball players, people can't tell if we're good or not. I mean, if everybody looks at LeBron James, they know he's a great basketball player, right? But it's very hard to judge, is a scientist brilliant or is he off his
Oh, imagine a basketball league where they never played games.
Yeah.
Where there was
all
no
people
scoring
ever did
system.
is, so there's a thing in martial arts. So all martial arts become performative.
Mm.
Like there's actually a website, I forget what it's called, it's really funny, but so somebody's a great martial arts master and he knows how to fight and wins and he starts a school, and one thing they do is they teach forms. How do you get all the things? And then some martial arts evolve to the point where they're entirely performative.
Like wushu is like this, right? It's like
and
very artistic.
then there's this thing where the MMA guys, which is all competition,
Yeah.
almost always beat all the martial art black belts in actual fights.
Right.
And some of them are the point of, you see somebody throw somebody in some martial arts and you can tell the person being thrown is literally jumping. And so let's imagine, modern science is at some stage of that journey to performative.
So maybe we need to figure out how to get a court, right?
Well, the court is innovation and production of tools that are born from the science.
And
This
that's
brings us to
the
where
engineering science divide is
Right.
you hardly ever engineer a bridge you're not going to build.
Right.
Like you could do it for a hobby. Like there are people who study bridges and, they create them in sim worlds and, it's fun. But, that's a small number of individuals with no money behind it. Like there's no large performative engineering projects.
Now, I did want to talk one more thing about, since we had talked about planets, in the modern theory, you have this protoplanetary disk, right? So what happens is you form a star and then you're leaving behind residue of this disk. Well, what is happening in your idea? You've got gravitational collapse to form a star, but not so strong of collapse that you can leave a disk behind, and then you permit that disk to then form the planets. It doesn't make sense. Like if you have got gravitational collapse, it's either all collapsing or it's not collapsing. It's one or the other. How are you leaving the planets behind to make your so-called protoplanetary disk? I'm not saying that such disks don't exist. I object to the word. Protoplanetary puts a bias in people's mind immediately that this is a disk that's going to be used to form planets, right? It has maybe nothing to do with planet formation whatsoever. So the term protoplanetary disk is a bias.
Well, so this still connects to engineering because I'm like, okay, well then if you're gonna build a planet, if you're gonna build a large structure of some kind, there's gonna be some theory that informs the process by which you do that. If we assume, like in the sci-fi future where it's possible to build planets, some theory will be the theory that acts as the basis. Or if you're gonna build a fusion reactor, you need to build a fusion reactor on the basis of science that works, because anything else that you try will be billions of dollars worth of failure. And so I feel like inevitably, as basic science becomes developed into something that can then be launched into the sphere of engineering, engineering is the MMA of the sciences, ultimately. Which is weird because so many people want to remain as basic scientists, where they're like, we're just looking out onto the world and we're just cataloging and examining and...
Well, and then curiously, in some science projects, the engineering they do is interesting. So I've met two scientists working on quantum computing who think, after years of working on it, decided it's mostly nonsense. But the engineering projects they did in the pursuit of, getting qubits to be, interlinked was really interesting. So you have to cool down an atom, and then you have to move it to a position, and then you have to control it, and then you have to measure it. And those engineering projects are cool. Like I've reviewed a few of them, and I'm impressed. And then Sam Zuluv at Atomic and I were talking to two guys working on a quantum computing thing. And we started making a list of the physics tricks. Like you can cool an atom with a laser with the right frequency because you can stimulate emission of a photon. So we had like 25 really cool physics tricks being used in support of building this quantum computer, which was going to get 20 qubits in harmony. And everything about it was cool, except the fact that once they had it, it probably wouldn't do anything. And it's viewed as a step on the journey, because there's a recent big announcement by both Google and Microsoft where they announced this big forward step, but it actually didn't do any computation.
Yeah, I'm
Right.
really skeptical of the
It's-
idea that the science will be proven out by the technology that results from it. I think that a lot of this, we're masters of electromagnetism, and nobody knows what electricity is.
Yeah.
Right.
And
So,
like the particle colliders, they're miracles of magnetics.
right. They're
Like,
just
it's so great that they can build a loop kilometers in diameter, accelerate charged particles, keep them accurately aligned. It's fantastic. But the result is like, well, what did they learn? Well, they learned they need a bigger collider, because they've usefully ruled out a couple more wrong theories. But that doesn't make any sense, because there's an infinite number of wrong theories. And
Now they want a much, much bigger collider now in
Yeah.
Europe, right? What is the size? It's much, much bigger than,
Oh wow, I didn't
Which-
know that.
than
which-
the large.
it interests me because, there's a funny thing here. I really like professors who teach, students how to think and learn. And I hire lots of interns, and it's really useful. And very often the professors who are really good teachers have projects which don't really have a, let's say, advanced science output.
Sure.
But they're also good teachers, and they create an environment where the students learn a lot, and then I get to hire them. And that's taking a relatively small percentage of, let's say, science and engineering potential offline, because they're producing stuff. But the big super collider project sucks up a big portion of the national science budget, and then a large proportion of physicists and engineers to go build the thing, and then has relatively few useful outputs, aside from the fact that they need a bigger one.
Yeah, I think
And this is a weird cycle, because then I think it's negative, because I look around and I see infinite numbers of engineering projects to be done that would be really great if more people were working on it. And then in the world of abundance and plenty, having a good percentage of your really smart physicists doing, relatively useless projects, seems like a bad thing.
I'd like to see science money distributed more evenly. That's for sure. There's too many professors that they have a paucity of money. They're unable to get funding and execute any of their ideas, and then some few professors channel millions and billions of dollars into one area. So I think there's a cost for that, because you could have very creative people that are not able to get funded, because you've channeled all the money into these large projects, right? And there in the large projects, you also don't have enough autonomy. So the people who join the large projects, even though the project seems great, you don't have that creative independence anymore, because you have to work in this big machine. So I think there needs to be a move away a little bit from large projects. And I've actually been thinking that we should reallocate funding. Like right now, and Harvard won't be happy as I say this, but Harvard gets a huge amount of the NIH budget. Okay. And I think that money should be redistributed more evenly across the states. That we should look at the population of the states and encourage professors to move to states across the United States, so that, a state like Iowa or Missouri gets more NIH funding, and not everything stays all at Harvard. It's not true that
the
just
funding should be inversely proportional to the size of your endowment. If you already have $100 billion, more money clearly won't help.
I think there's a ton of hope in these small new institutions. There's a really interesting anecdote here from MMA, actually. You were talking about how these traditional martial arts become performative over time. What's freaking crazy is that somewhere back in the 90s, a family developed a martial art on their own, essentially, that completely trumped every other martial art on the planet. It was brand new. It was called Gracie Jiu-Jitsu. And they showed up on the scene and literally dominated everybody. These skinny little guys were tapping out these huge behemoths, right? Who had every single martial art was completely dominated, because somebody had a really good idea and developed it. And they realized that there was a way to actually approach the whole process of competitive fighting in a totally different way that didn't involve standing up and taking swings at each other. It was literally just about limiting the motion of your opponent, essentially. And so that's a really exciting and hopeful possibility for the future of science, is that if somebody had a method that was actually productive, obviously some of us hope to, and you created a training pipeline to teach people to think in that way and to work in that way, you might actually be able to outcompete these giant behemoth.
Well, one of the things that's happening is there is internet today. I was thinking the other day about Halton Arp and his paper about seeing red, his book, Seeing Red. And he was a brilliant man. And I had written to him and I said, next time you write a book, you might not, he put his emotions in his book. Like he was upset with a lot of people. And I told him he probably shouldn't have done that. But he didn't have the advantage of internet. Today, it's a different world because as we speak today, we don't know who's going to look at it. Who might say, oh yeah, there's some good ideas here that we need to pay attention to this. So that's an advantage that Halton never had. So astronomy has always banked on the fact that people who come up with ideas that they don't like will eventually die. And the idea dies with them. But that's going to be a very different world now because in a few years, I'll be dead. But a lot of these videos, if society survives, will still be there. And people will be able to learn the things de novo. It's like, that's why I do videos, because you're able to teach. And once each video is covering some aspect that I'm trying to get people to understand and to master. So that stays. And Halton never had that. He could write a book and you'd read the book and how many people are going to buy it, right? But on a video, you could have thousands of people going and starting to think about it. They start thinking about the problem. And once people start realizing that, oh, maybe the sun does have a surface, it's like, if you see something beautiful, you can't take it out of your mind anymore. In my case, it's my wife, It's like, you just can't take it out of your mind, right? Once you see her, it's over. And science is that way too. Once somebody comes to learn that the sun has a surface, they cannot take it out of their mind. They will always look at it and say, maybe Pierre's right. It's not an optical illusion. There is a surface there.
And then it goes I'm sorry.
I was just going to say, this extends the metaphor of the jujitsu school that figures out a different way to fight and then is able to accomplish things that nobody else could do. And this is why I think that science does feed into everything that's downstream of it, because if you understand something from a different viewpoint, if you can stand somewhere and see something different than everybody else sees, you suddenly have this breadth that opens to you that was inaccessible before, because if you're standing there and you're like, well, the only thing that I can do is go work at a particle accelerator or build another particle accelerator, and that's going to be the only path forward to me, you're going to be like those behemoth dudes in the MMA ring that are getting knocked over by the skinny guys. Like the ability to stand somewhere and to see clearly something that no one else has capitalized on, that's literally untrammeled ground. That's where power comes from, to be able to actually change the world, I think.
And sets an example for so many other pieces of science too, right? Because if that big of a change can happen, and I agree that I believe it will happen, but when that happens, that will completely inspire God knows how many innovations.
John Wilkins had once, now I made a little video on John just before Christmas. So if you want to know who John Wilkins is, just go to my Sky Scholar channel and you can see a video on John. But he had told me, he said, Pierre, it'll be like an explosion. When physics finally comes to understand that the sun is condensed matter, it'll change overnight. It's not, I told him it would be a long process. It'll be a gradual change. And John said, no, it's going to be dynamite. Once they understand it's condensed matter, it's over. It's going to change very, very rapidly. So we'll see if John's right.
Literally a phase change.
Yeah.
Well, like tech has generated phase changes. Like it's interesting, like when they tracked adoption of PCs, Like they thought it would just be this revolution in productivity, and like 15 years in, it wasn't clear. Like people liked using computers and they did stuff with it, but the internet and then mobile phones was transformative. Like it really changed everybody's life. Like, and some funny things happened. Like there was this innovation race on digital cameras, and then once the camera got in the phone that was any good, the digital cameras essentially disappeared. Like there's 2 digital cameras here, but that's for a specific reason, right? Nobody buys a digital camera anymore.
And
Like
honestly, in a few more years, I think you won't even need these. Like cell phone cameras will be enough.
Yeah, be fine. So some technical innovations, like PCs were everywhere. There was PC magazines and people were buying, but if you went and measured business productivity, nothing happened. And then the internet got big enough, and then what they call software as a service and all these interacting platforms started to really transform what's happening. AI is kind of wild because the financial hype is so big, it's unbelievable. Like it's literally trillions of dollars of value. But it's already impacting people's productivity. Not in trillions of dollars kind of ways yet, but it's going relatively fast. And
Well, 'cause the
we just
infrastructure
barely
is
started.
Because the infrastructure is there already, right?
Well, they're scrambling on. So the infrastructure in terms of networking, internet and cloud computing and people's access to things was pretty good. Like everybody can get to a
Yeah.
AI model really fast. The AI models themselves are, they're scrambling to build out the infrastructure on today's models. But it's already impacting people's business because it's such a high leverage technology.
But it's like for the PC revolution, you first have to build the infrastructure
Yeah,
for the PCs. And now that you have the infrastructure, you can build something else on top.
Yeah, same thing happened with electricity. Like electricity evolution was scientists made generators, and then companies made custom power generators for, say, a factory. And then somebody made a bigger generator that could say, hey, build your factory here because you already have power. And then it started getting widely distributed. And so homes are being set up all over the place, but nobody had any appliances. So you'd wire up a house with 10 amps, right? And the first application was 5 light bulbs. And then they started to build appliances, and all of a sudden 10 amps is crazy. So it went to 60 and then 100. And nowadays, if you build a modest-sized home, you probably put a 200 amp service in. And now you just assume power's everywhere.
And I feel like this is like you said, it's the phase transition for science too. Like we have this vision of science being super, super advanced. And I don't think that that's necessarily true. I think the project is relatively short-lived. I think that we've been through a couple of generations, but it's still a really nascent process for understanding the world. It's like we haven't come that far. But we do have the infrastructure for how to think about it, like what it looks like to do an experiment, what it looks like to actually measure something accurately and reliably. And now the limitation is just the ability to see what we already know in a different way. Because you said something really zero-day science. Like that's so important because we talk about this all the time. The theory of electromagnetism, the theory for photons, like all of this stuff predates even atoms.
Yeah.
Like we weren't
like literally predates atoms.
Right? And so I'm like, well, obviously these things are crazy. Obviously we're wrong about
I'm an expert in medieval science.
Yeah,
exactly. And I use it every day to do stuff.
Exactly.
Like literally, there's a motor in your refrigerator that's 1840s technology.
Exactly.
Like it's refined a little bit. It's got 3D printed plastic in it. It's kind of wild. Like it's.
But I think that there's a lot to be optimistic about. And I think that, Pierre, your work is a big part of what there is to be optimistic about. Because you've gone out into this world and you have shown that it is possible to just look at it and to see things differently. And I think that that's what's so powerful about it.
Well, thanks.
This has been absolutely incredible, guys.
Yeah.
I've wanted to get you two in a room together for a very long time. And you're both two of my favorite thinkers in very different ways. And so I've really enjoyed, and thanks again for having us stay with you. And I'm looking forward to talking to you more for the rest of the day too, off camera. This is, by the way, people who are listening, this is just what we do anyways. We're just kind of letting you in on it. So I'm so happy to be here. And Jim, thanks for making it all the way out here as well. I know you have come several thousand miles to be here today.
I like to travel, apparently.
Thank you so much. Thank you, both of you, so very, very much. From the absolute bottom of my heart, this is really incredible.
Well, we figured out yesterday, I'm really curious about, science in general and progress. And then my brain has a detector when things don't quite make sense. And I read this paper 20 years ago that had 10 or 12 puzzles about the sun. And we figured out yesterday that Pierre wrote the paper. And the kind of my idea about, like, I hear so many times, this is impossible, and that's impossible, or that's hard, or why would you do it? And for me, that's kind of a signal, like, that's interesting. That's worth investigating. And, your journey of doing things is curious. And every once in a while you meet somebody who inadvertently, in a paper, like, changed how I thought about, like, literally physics. So thanks, both.
All right.
That's pretty cool.
That's amazing. Thank you both.
All right.
Bye,
Bye, everybody.